First of all, good morning, or we are just noon now, good noon. And you are welcome, all of you. And some people will join us afterward. And I would like to thank again Ustad Salim. He's always behind the scene and working very hard. And our guest today, our lecturer, he's member of the virtual university. He will give a syllabus, and today it's his day. It's the day I wrote for here. It's Wednesday, October 20, and he will talk about the current and future prospect of nanotechnology in the performance of solar thermal system. His name, Dr. Saleh Khamlish. He is Moroccan, young researcher, senior researcher, and lecturer at the University of South Africa. He is founder of Nano Energy for Sustainable Development in Africa. He will maybe give us some word about it. There is a link to this regarding this foundation. Just to say two words here, as he sent me his short bio. Senior researcher at the University of South Africa, expert in solar thermal system, Nano Fluids, and nanotechnology for the exploitation of renewable energy resources. He's graduated from Chuan University of Technology. I hope I spelled very well. Founder of Nanotechnology for Sustainable Development in Africa. I already said this. It's an initiative which is a program focusing on promoting the sustainable of renewable energy ecosystem to ensure social economic development in Africa. I want to thank him for being with us, for being engaged in the virtual learning university, and the floor is yours, Dr. Saleh Khamlish. I will leave the screen now and stop my sharing and let you you share your presentation. Okay. You start.
First of all, thank you very much, Professor Nawi, for this beautiful introduction, and I'm really honored to take a part of this initiative, the Virtual Learning University, which is something I recognize it as the best way of educating our people in Africa and the Arab world. Since recently we were facing this COVID pandemic, and it was a challenge for education. So I think this kind of initiative will help us as researchers, as scientists, to spread our knowledge to the new generations and to the next generations. So I will share my screen now, so we will be able to, okay. So can you see my screen?
Yes. Yes.
Okay, thank you very much. So today, and as Professor Nawi mentioned, I would like to not to discuss really about only solar thermal systems. What we would like to do today is to show how nanotechnology could contribute to the development and to the enhancement of efficiency of these solar thermal systems. Of course, my title is Current and Future Prospects of Nanotechnology in the Performance of Solar Thermal Systems. So today I'm going to share with you what it was done so far and what we can do in order to enhance the performance of these kind of systems. My name, of course, Dr. Saleh Khamlish. I am a senior researcher at University of South Africa here in South Africa, and also a founder of Nano Energy for Sustainable Development in Africa. Actually, this initiative, it started with my colleagues here in South Africa. It started in a funny way, I can call it. We were sitting as emerging scientists and discussing the benefit of science in Africa. So we found it difficult, really, that our youngsters and students, they embark on theoretical studies and stuff, but at the end of the day, they are not able really to take the fundamental to the real life. So the NISDAF, it was born from there. We're trying to use this initiative to attract students, particularly who are dealing with renewable energy projects, so we can show them how they can convert the theory that they are studying at the university level or other schools of engineering and to take it to the real life. So this is actually the reason of the NISDAF. And I hope our colleagues from Morocco will also benefit from this. And of course, I'm thankful to Professor Nawi who really showed interest in this, in our activities. And hopefully in the future will also contribute hugely to the Moroccan development in solar energy. So let me go to the next slide. So let me just show you what I'm doing here in South Africa. So I came in South Africa in 2010 here. As you can see here, I was very young and I was studying here at Eczema Labs. That is the title, as you can see there, Eczema Labs National Research Foundation. Actually, Eczema Labs is a national facility founded by the South African government. They give fund for researchers to embark in research related to different aspects of research, from particle physics to material science to biological science to different things. And they have state-of-the-art accelerators there, like this one that you are looking at here, Electron, where you can accelerate particles or protons in order to study materials. As you know, protons, when they interact with, let's say, 10 films, so now from extracted energies or the scattered protons, you can know exactly the elements in your materials. And these techniques is very important because sometimes when you are dealing, let's say, with solar cells and film, and now you are facing the problem of the purity. You have contaminations or whatever. So with these techniques, you are able to detect if there are some kind of contaminations in your system. This is one of the applications of the accelerator that we have there. So of course, the center is beautiful. We have some nice animals there, as you can see there. Always when we are tired from science, we go down there and we are inspired by nature, of course. And there is a nice penguin there. So always I visit this one around Cape Town here. And of course, these are some students that I am lecturing and training here at Eczema Labs and also at other institutions. This is when I was student here, I am contributing to the South African development when it comes to research and development and renewable energy systems. So the question that we have to ask always, why solar energy? Of course, we have to motivate youngsters and emerging scientists. More than 50% of the global energy by 2050, it should be coming from renewable energy sources. And the most and the vast majority should come from solar energy, of course. So this is the first motivation, because we are facing huge dilemma when it comes to, let's say, climate change. So as scientists, we have to answer that question, what can we do in order to avoid this climate change? And of course, if you are following the news recently in Europe or even other parts of the US or Asia, many countries, they were having huge problems due to this climate change. So as scientists, we have to come up with solutions. Of course, to solve the energy crisis, this is what I was mentioning, to create job opportunities, because doing research is beautiful, but now we need job creations. And I believe through our research in renewable energy and from Moroccan point of view, I think the Morocco, it showed that it is doing very well when it comes to creating jobs related to renewable energy applications and so on. Of course, more energy is better life, and Africa, it's still having huge issues, as you can see from this map. So, as I mentioned, job creations is very important. So according to Google and Vivid Economics, these are international organizations. So they estimated that in the sub-Saharan Africa, and also in Asia, it's almost 372,000 full-time equivalent jobs were created. But The issue, as you can see here, almost 56% of these jobs are located in rural area, and also let's say 27 from these jobs, they were made for women. But the dilemma again is Africa. As you can see clearly here, if you look at Asia here, China, it's almost 4 million jobs were created by embarking in renewable energy research. When it comes to Europe, it's almost 1,235,000. The Brazil is almost, if we compare it with Morocco, we cannot say they are highly advanced than us, but the question I'm raising now is why Brazil, they are creating more than 1 million jobs, but Morocco, it's still 29,000. This is in 2018. South Africa, 66,000. So Africa, it's still suffering. They are embarking on renewable energy, but job creation, it's still low. And we have to think about this also. And when I'm saying we have to think about this, if you look at the map, which is coming from this organization, so you see that Africa, it's really beautiful when it comes to solar radiations. It's almost 2,000 kilowatt per hour per square meter arriving as irradiation to Africa. Africa, it's really the best continent which could really be used to develop technologies related to solar, thermal, or photovoltaics, of course, to solve the problem of energy and also job creations. From the previous slide, we saw that China, they are creating more than 4 million. So now what is the problem of Africa? So what is exactly the issue? Of course, Morocco, I'm very proud to see that Morocco, it's really investing hugely in these technologies. And I believe that in the future, Morocco will be one of the leaders in the world in that regard. Europe, they are not like us. We have more energy, but Europe, they are doing much better than us. They are creating more than 1 million jobs only from renewable energy. So really we have to sit down and think as African scientists, how can we contribute to developing our continent and using this fantastic radiation and energy from the sun and creating jobs for our youngsters, for a better future for us. Even the Middle East, of course, Saudi Arabia, Bahrain, and other countries are doing very well. Of course, Emirates, I'm very happy to witness that because there they show that they made a smart move. We cannot rely on petrol. Petrol, they will go one day, maybe after 50 years from now. So what are we doing exactly? So thanks to Emirates and Saudi Arabia also who showed interest in these kind of technologies. So when it comes to solar or the types of solar thermal collectors, I believe most of our colleagues today, they knows exactly what is there exactly. So we have mainly what we call parabolic true reflectors. We have linear Fresnel reflectors. We have what we call parabolic dish reflectors. We have towers. Of course, these technologies are, we cannot say it is a rocket science. There is nothing here difficult. For example, when it comes to parabolic true reflectors, you design very nice polished mirrors in a parabolic shape. You have a receiver which is coated by a material which can absorb the reflected light by the mirror and convert it to heat. That heat, of course, is used to produce electricity. I will show you in the next slide how, for those who doesn't know this technology. For linear Fresnel reflectors is almost not the same, but here you use mirrors to reflect on a tube receiver, of course. It's the same principle, but the mechanism is different from this one. For a parabolic dish reflector, they use sometimes Stirling generators and stuff like that, but the cost is too high. For the tower, of course, the cost is high, but the efficiency compared to these two, it's much better. I will share with you more information while we are going through the slides today. So in this slide, I'm not gonna discuss all the solar thermal, but I'm gonna just show you the parts used in these systems because it's very important for this talk today. Because as I mentioned in the title, I'm gonna discuss the contribution of nanotechnology. So it's good for us to know what are the parts used. For example, if we take this sample system, which is a flat plate solar heating collector, which is used everywhere, I can say, for geysers, to heat water, to take showers and stuff like that, and at every home. And so this system, what it has, I'm gonna speak about the most important parts. It has an absorber plate, which is there, and that is, as I can say, the core. That is the one which really take the sun radiation and convert it to heat. And of course, we have the fluid in, or the heat transfer fluid, which is heated by the heat which is coming from this absorber plate. Of course, sometimes they put covers, glass covers, to avoid irradiation and to enhance the efficiency up there. Insulation, because you don't want the heat to go down. You want to make an enclosed system. So in this talk, I'm going to show you how can we, by using nanotechnology, how can we enhance the performance of these absorber plates? And of course, how can we use different fluids to produce high heat transfer in order to have higher efficiencies? When it comes to evacuated tubes, of course, the mechanism is different because here you use evacuated tubes where they have these plates. Of course, they are coated with materials which can absorb the sun radiation and convert it to heat. And that heat, it is transferred to heat what we call the heat transfer fluid. And of course, again, I will call it, this plate is a core, because that is the most important, because here you are interested by converting the sunlight or photons to thermal energy. So we have to be sure that these plates are highly efficient. And I will show you how to do that during this lecture. Of course, when it comes to a parabolic through, of course, as I mentioned, you have a mirror. Mirrors, they have to be highly reflecting, more than 90%. And these mirrors, we can make them locally. And we have done that, of course, here in South Africa. We are making these. And of course, once you have good mirrors with high reflectance, you have what we call a tube. And this tube, again, is coated with a selective solar absorber, the material which converts the sun radiation to heat. So now, once you convert the photons from the sun radiation to heat, you need a highly efficient heat transfer fluid to be able to use that heat for your applications in terms, if you would like to produce electricity, or if you want to use that heat to do pasteurization or different applications. So now, if you look at this system, which of course I'm gonna also speak about it more in this lecture, you have to make sure that your absorber coating and the heat transfer fluid are highly efficient. So there where nanotechnology will play a role. So here, I'm just gonna give you these nice pictures to show you what I was speaking about. These tubes, for example, for this system, they look like this. You can buy them from the market, of course. I'm not sure if they make them here in Africa, but I didn't see some companies making them. Almost they buy them from China and Europe and so on, but they are very easy to make. Because if you can make a selective solar absorber, as I showed you, which is coated, and if you can make a very good heat transfer, well, you can be able to make them locally. You don't need really to buy them. And imagine in Morocco, we have a very huge CSP plant. If we can make this, we will reduce the cost. Of course, when it comes to a tower, of course, the core is the absorber there at the top. And again, this absorber, it's coated with a selective solar absorber. You cannot coat it with a black material because black material will have huge emissivity and the efficiency will be reduced at the end of the day. So we have to think about these parts, which are the cores. So now this is where nanotechnology will play a role. So again, if we take a case of a parabolic true plant, like what we have in Morocco, the principle of these systems is very clear and easy to understand. As I mentioned, you have a mirror, you have a tube coated with a selective solar absorber heat transfer fluid. It's a very easy mechanism, and the configuration is there. I showed you here that we need a highly effective and efficient selective solar absorber coated on the receiver tube, and we need a highly efficient heat transfer fluid. So nowadays, they use mainly oils, or sometimes they use some conventional heat transfer fluids. Of course, liquids, they have low thermal conductivity. To enhance the thermal conductivity, you have to introduce what we call nanoparticles. Because they are solids, they have higher thermal conductivity than the liquid. And automatically and normally, by adding nanoparticles, you will enhance the thermal conductivity, and of course, you will enhance the heat transfer. I will share more about that. The system is easy here. So the plant, it looks like this. You have different mirrors like this, which are here, and parallel, and series also. So if you have more of them, you increase more, you have more energy coming out. So for example, the heat transfer fluid, which is used there, it can, the temperature can rise above 350, which is there. And that temperature, it will move, that heat transfer fluid will transfer the energy, which is a form of heat. It will transfer it to a system where we can really use a heat exchanger to store energy for the night. And of course, we can use it, of course, to create steam. This part to store energy for the night. This part is to create steam. The steam will turn a turbine to produce electricity, and so on. So that's why I mentioned that the heat transfer fluid, which is there, and these selective solar absorbers are the core of this system. If you have high efficient selective solar absorbers, which can convert the light to heat, if you have high efficient heat transfer fluid, you will increase the efficiency of all of these plants or this system, and you will have better efficiency. Of course, as I mentioned at the beginning, I'm proud that I'm a Moroccan and I'm witnessing what is happening in Morocco. We have the biggest plant in Morocco, the Nor Ouarzazate. Beautiful. Annual net output is 370 gigawatt for the Nor 1, 600 gigawatt for the Nor 2, 500 gigawatt for the Nor 3. But do you believe that we are getting this capacity? I don't believe so. Because there are different parameters which can impact this plant, and it's difficult really to reach these capacities. So we have to think, how can we reach these capacities, or even maybe going above these capacities? So by involving nanotechnology here and creating new materials, I believe that we can reach these capacities, or even maybe going above these capacities. By using what we call selective solar absorbers, or new generation selective solar absorbers and films, and by using new generation heat transfer fluids or nanofluids, where nanoparticles will play a huge impact on that systems. What we are looking for here is quality, speed, efficiency, and cost reduction. So this is our aim. And this is what we want to contribute to, how we want to contribute to the development of these kind of systems, particularly in Africa. So that is the introduction on, let's say, solar thermal systems. So now let's move to nanotechnology and how nanotechnology could really contribute to the enhancement of these solar thermal systems. So what is selective solar absorber? That's the question. And by the way, I'm very grateful that I will be involved in contributing lectures at the VLU. So today I'm just gonna give you a flavor. But during the courses in the future, I will explain very well how these systems work from the theoretical point of view to the experimental and the application. But today, I'm just gonna give you some, a flavor, just to understand how this system works. So if we look at the solar radiation from this curve there, if you measure the solar radiation, this is wavelength in the micrometer, and this is the normalized radiation power. Of course, the sun radiation, which we are interested by, it's located at this region from, let's say, 0.3 micrometer to 2.5 micrometer or 3 micrometer. And that is the peak of the solar radiation that we want to absorb with the selective absorber, because this is the photons which are located there, or this power from the radiation, that is the most important, which can be converted to heat. Now, above, let's say, 2.5 micrometer, we have what we call the near infrared, or the near to the mid to the high infrared. So a selective solar absorber, it will allow you to absorb highly this energy and to reflect the IR. And that is the configuration. You need to design a thin film which will be coated on the receiver tube or the tower that I showed you, which have these properties. It has to absorb mainly the visible light and the small portion of the infrared, only to 2.5, but the rest it has to be reflected. Why? Because the infrared is heat from the sun. If your material is heated, you will lose energy through emissivity, and you don't need that. That's why I told you we don't need to use black bodies. A black body, it absorbs everywhere. It absorbs this region and also in this region. And you don't need to use that because the efficiency, it will be very low. So you need to design a smart material which can absorb only this portion and reflect all this portion which is here. Because that portion here, it will cause it to be heated up and you will lose energy through emissivity. So what are you looking for? What we are looking for exactly? If we take the configuration, the absorber, it has to absorb at least 60% of the sunlight in that region, in this region here. To be able to do that, of course, you use a cover, glass cover. Why use glass cover? Because the heat, of course, or it's gonna be, you will lose the energy through what we call convection or reflection or radiation. If this selective solar absorber, if it is heated up due to the absorption of the infrared, you will lose a lot of radiations. And that radiation, you need it because you need to heat the materials that you are, or the heat transfer fluid, which is gonna be up down here in the tube. So the reflection, you will reduce them by introducing a glass cover, of course. Of course, convection, if you want to avoid convection, you need to create vacuum, because if you have molecules, they will contribute to the loss of energy or the radiation. So you have, when you are designing your system, you have to take in account all these parameters. And there is a beautiful equation here. It shows you clearly that if a selective solar absorber, if it is heated up, that is the temperature of the selective solar absorber, and this is the temperature of the environment, power 4. And this is the area here, Boltzmann constants, and also the emittance. So now, if the temperature of the material which is used to absorb the sunlight, if it goes up, of course, you will have huge thermal energy radiated outside of the system, and the efficiency will go down. So now we have to be careful. We have to use this kind of equations carefully, and we have to design a system which allow us at least to absorb almost 60% of the sun radiation and to convert it to heat. So selective solar absorbers, you can make them, and there are different configurations. So if we are trying to design these kind of materials or thin films selective solar absorbers, we have what we call intrinsic materials, materials which they have unnatural properties in absorbing the sunlight and convert it to heat. You can deposit a layer, an intrinsic layer which have this property on a metallic substrate, and you can have this property of absorbing the UV visible and reflecting the IR. The next configuration is you can use semiconductors materials or metal tandem, where you use an anti-reflecting coating on the top. You have a semiconductor which allow you to absorb the visible region of the solar spectrum. And of course, down there is the metallic substrate, because the tube that you are using, the tube where you have, as I showed you in the previous slides, of course, it has a metallic material, is a metallic tube, is coated with that material. So this configuration also, it can work. Of course, you can use multi-layered interface stack, where you use, like, let's say, dielectric, metal dielectric. When I say dielectric, like metal oxides, like chromium oxide, for example, or let's say nickel oxide. You put another metallic layer, that metallic light help you to reflect the infrared, because metals, they are very well known at reflecting the IR. And you use another layer, which is a dielectric or a metal oxide, which has a property of absorbing in order to enhance the absorption more. So this configuration is also smart. You can use cermet. Cermet, it means that you have a material and you have nanoparticles embedded in that material. So particularly they use plasmonic nanoparticles or metallic nanoparticles, because they are very well known that they absorb the visible light. So you can use them in this configuration, of course. Sometimes you can also think about textured surface coating. You can take a thin film or a metal and you can create pores. Imagine with me now, let's say the visible region is between, in the solar spectrum, it's between, let's say, 370 nanometer in wavelength to 750 nanometer in wavelength. And if you can create nanostructures in a metal with porosity below 700, let's say 1,000 nanometer, let's say. So the wavelength in that size, they will be able to penetrate those pores and they will be trapped and converted to heat. So the rest, the bigger wavelengths, which they cannot penetrate these pores, they will be reflected. And this is also a smart design. And we are also trying to do this kind of research here in South Africa. Of course, you can use selective solars, transmitting coating on a black body. For example, if you are not able to create, let's say, smart material as a selective absorber, you can use a black material which absorbs everywhere, and you can coat it by what we call smart mirrors or heat mirrors. Heat mirrors, they allow the light to pass at the visible region, the UV visible region, and they will reflect the light and the infrared. And now you have a smart configuration, which allow you to have high absorbance and low emittance. And this is what we are looking for. So here at Tempa Labs, we use different techniques. And I'm sharing with you this technique now. We call it electron beam evaporation, which can allow you to create 10 films like these ones, multi-layered interface stack, or it can allow you to create this configuration. of course, it can allow you also to create this configuration by using electron beam evaporation. So what is electron beam evaporation? Very simple. You have a tungsten filament. That tungsten filament, if you put very huge voltage, you force, because it has resistance, you force the electrons to jump and to come out, highly energetic electrons. These electrons are deflected by a magnet. This is physics. They are deflected, and you have your target. For example, if I'm going to deposit chromium oxide like this configuration, I put a target of chromium oxide here, and the atoms from that target, they go to the substrate, which is metallic substrate. And these atoms, in the form of a plasma, a gas, because these electrons are highly energetic, they will create a plasma, they will evaporate, they will melt and evaporate your solid target and create a plasma. A plasma is a form of gas, atoms in a form of gas, and they will go up and they will be deposited on a substrate. So you can create our system here as Tempa Labs. We are able to put 3 targets, or 2 or 1, whatever what you wish, but the maximum is 3 targets. So I can put a target of chromium oxide, I can put a target of chromium metal, and I can do co-deposition. And at the end of the day, I will have something beautiful like this for studies. Because here, this is fundamental. We have to study at the lab before taking it to the industrial level. So I deposit in a small substrate like this, and I will have something like this. Stainless steel substrate, a dielectric, which is chromium oxide, a metallic layer, another dielectric. And from there, we have to study this to show that our claims are true. If we make a configuration like this, it will give us high absorbance and lower emittance. And this is what we are doing. We have at the lab a very beautiful spectrophotometer, which is equipped with an integrated sphere, which can allow you to do what we call diffuse reflectance. Remember, why we do diffuse reflectance, and sometimes we can do also specular reflectance. Diffuse reflectance because the sun radiations coming from the sky are diffused everywhere. Even when they come to your material, they are scattered. So the photons are going everywhere. So now you need to have a sphere which can reflect those photons, which can be detected to give you this information. So what I was mentioning in the previous slide, that we need to absorb hugely in this region of the visible. And our configuration, of course, it is absorbing nicely in that region, as you can see. And it is reflecting nicely in the infrared, which means this material is smart as a selective solar absorber. If it is absorbing everywhere, it is not good for those kind of applications in solar thermal. And this is nanotechnology, because here you are dealing, of course, with a tin film. So the thickness is at the nano range. It's below 40 nanometer of this one. This one is below 10 nanometer, and the other one is also below 40 nanometer. So, and the thickness, of course. So this we can call nano tin film, and this is nanotechnology. And the material, it shows very beautiful behavior in terms of reflectance. It reflects very low here, and it reflects highly in the infrared, which shows that it can be applicable. And there are beautiful publications we published recently, 2019, 2018. You are more than welcome to read more about this. So again, it's not only about optical analysis. Of course, here you show that it is reflecting, it has lower reflectance at the visible region, the near IR, and it has higher reflectance at the mid IR and above there. But no, for real applications, so how much heat is generated by that material or this material? How much heat is generated? So because, of course, we are in Africa, it's difficult to buy systems because of the lack of funding. We have to be smart sometimes. We have to design our own systems. And we are lucky we have these open source systems like Arduinos. I believe many students, they are very familiar with this kind of technologies. These are very cheap technologies because they are open source and you can use them to design systems at the lab in order to study your material. So what we have done here, we created the solar light simulator. And of course, we use this configuration. This is a thermocouple. So what we do, we send the light at the visible region, and we are trying to find out how much heat it is generated and reading that heat in our computer. So, of course, some people, they will say, maybe the heat is coming from the light. No, this light, we put it above. The heat is not coming to the system. So we made sure that the heat is not coming. We have done this analysis in air without putting a glass cover, just in air, just to find out if our configuration or selective absorber, if it is good or not. So what we have got is this. As you can see here, this is the surface, the stainless steel. That one, let me go back. That is the stainless steel without the coating. Is this one. The blue line. The dark line is our configuration, chromium 2 oxide 3, chromium 2 oxide 3 on stainless steel. Stainless steel, of course, because the metal, it didn't absorb, so there is no heat generated. This is the temperature generated that we sense it with our developed system, with the solar simulator. This is the time. So, of course, the stainless steel will not, because it's just a metal. So now our system, it shows that by shining the light on, the temperature is rising, and it achieved 180. And when the light is off, of course, the system, it starts to cool down. Imagine with me that configuration, it gives us more than 180, I think 190, just in air without, we haven't done this experiment in vacuum. Just imagine if we will do it in vacuum, because of course, if you do it in air, you will have some kind of loss of heat. So I believe by doing this experiment in vacuum, and we are planning for that, we will arrive even to 300 or above, which is beautiful. So from this measurement, we managed to calculate with this equation the efficiency of the system. And we found that the blue line here, it shows the total efficiency. We found the efficiency of the system at 180 degrees. It's more than 50%, which is beautiful. It's very nice because the experiment was done in air, and I believe the efficiency will be much better if we can be able to put the system or isolate the system by introducing the vacuum or covering the system and having vacuum to avoid what we call losing radiation through convection. So here, what I was showing you, we can use this material that I was showing you to be deposited in the tubes that we are using in solar thermal systems. These are tubes, so we can deposit it like this way, this configuration. Of course, we can, deposit an intrinsic material that I was showing you on that previous slide on a tube in this fashion. Of course, we can make structures on the tubes or pores, as I mentioned, which the light can be trapped and converted to heat. So now, by comparing these three configurations, if I coat this tube with a black body, of course, the material, it will have high absorptivity, but high emissivity. To reduce the emissivity, we have to coat again this with what we call a heat mirror to reduce the emissivity. The configuration I was discussing, it has high absorptivity and low emissivity, according to the optical analysis that we have done, that I showed you before. Of course, this configuration is not easy to make because you have to use what we call lasers to create these grooves, or otherwise you have to select a suitable etching method to create what we call nanopores or whatever on the surface of the metallic tube. So this configuration, because if you control the size of the pore, you will have what we call high absorptivity and low emissivity. So these are three configurations that, of course, we would like to embed in our systems and hopefully in Morocco in the future. So here I'm suggesting, because what I was saying here, to make this you need electron beam, and electron beam, the cost can be really high sometimes. To make this, of course, if you use lasers or wanted to create grooves, it can be costly somehow, but this it can be made, of course. It can be made at lower cost. But we can, I designed this system recently, and we can do what we call chemical etching. If I have a tube, I can etch it, and I can create a black material or pores in, themselves, which can help us to absorb the light, the desired light that we want to convert to heat. So hopefully this will be this will be accepted soon, so we can embark in this research, and hopefully this research, of course, will go to Morocco, so students, they will benefit from it for their PhDs and master studies. So I will share more in my syllabus and my future lectures on this business and how you can do etching, how you can design these systems, and so on. So now, after discussing about selective soil absorbers, which are, of course, the core of these kind of solar thermal systems, now I'm going to move to what we call the heat transfer fluids or nanofluids. So as you can see in my lecture, I am covering two parts, which are the most important: selective solar absorbers and heat transfer fluids or nanofluids. So the second part will cover the heat transfer fluids, as I promised. So in this slide, what I'm showing you here is some solar thermal fluids which are used recently. We call them conventional heat transfer fluids. Of course, the most of the parabolic or CSPs, which are based on parabolic configuration, they use synthetic oils. Of course, synthetic oils, they are good because they can resist temperatures between -50 degrees to 340. But imagine if you add nanoparticles to these synthetic thermal oils, maybe you will increase here. You see, and there where nanofluids will play a role. Of course, if we are talking about molten salts are used in the towers, because the towers, the temperature can go very, very high, above 800 degrees sometimes. You cannot use a synthetic oil because the degradation will play a huge role there. So molten salts are suitable for those applications. Again, molten salts, we can add metallic nanoparticles to them, and we can create nanofluids from the molten salts. And we are trying to do that with some Europeans recently, and hopefully this project will go nicely, because we believe that will contribute hugely to enhancing the efficiency of the towers. So there are ionic liquids. There are some systems they use gases, which is fine, vegetable oils or whatever. So nanofluids. Nanofluids is the future of these systems. And that's why students at our universities in Morocco who are involved in or embarking in research related to solar thermal systems, they have really to learn more about this business. Because I believe Morocco, it's one of the first countries, I think, in Africa who embarked in these technologies. And we have to create opportunities through creating research and development related to these. So we can create jobs and students can be able to have the know-how to do this. So nanofluids, of course, you can use any conventional heat transfer fluids or even molten salts. And you can introduce nanoparticles in synthetic oils, ethylene glycol, even in water for lower temperatures, like the solar plate, solar thermal system, the plate one, or the molten salt, of course. So I don't believe, we have done the research, and there are thousands of publications Recently, we are trying to understand the mechanisms how nanoparticles they contribute to the heat or the thermal conductivity enhancement. So I am interested, and the researchers I'm working with currently are interested by this. And we are trying to create highly efficient and highly stable nanofluids, which they could be commercialized and use it for the development of our continent when it comes to solar thermal systems. So of course, when you are dealing with heat transfer fluids, you have to take into account different parameters. The maximum temperature, because you don't need degradation. The freezing temperature, because if you are working in the countries where the temperature can go down, so you don't need your heat transfer fluid to be freezed. The density, of course, because the density have relation with the temperature, it can change, and it can impact the pressure of the system, and it can make some troubles for your systems or solar thermal system. The steam pressure, of course, because you create steam in a parabolic system or even the tower or whatever. You have to take all of these things in account because the pressure will impact the heat transfer fluid at the end of the day. The specific heat, of course, you have to make sure that your specific heat is controlled and optimized. The enthalpy of the system, the viscosity. So there are different parameters that I'm going to cover during my lectures in the future to show what is the impact and how can we do calculations to make sure our nanofluids are suitable for these solar thermal systems. So what is nanofluid? I was speaking about it, but nanofluids are not really used only for concentrated solar power. Nanofluids, if you really have the know-how, you can make them for different applications. Refrigeration, heating and cooling of building, engine cooling in your car. Sometimes you go and you buy coolant for your car. And these coolants are made from ethylene glycol. So imagine if you add nanoparticles to this coolant, of course, the efficiency will be much better. Even the oil you use in your car. Recently, there are researchers trying to add nanoparticles to the oil because they believe that will help to increase the lifetime of the engine, because these nanoparticles will polish the engine from the inside automatically, and they will contribute in cooling the engine even. And nuclear systems, of course, because even a nuclear system, if you want to use it to produce electricity, what you are doing, it's similar to a CSP system, but here you are using nuclear energy to produce heat. And that heat, it has to be transferred by a heat transfer fluid. Now researchers around the world are developing nanofluids for nuclear systems. But in our interest is solar energy. And that is what we would like to develop. So what is nanoparticles? Of course, for students who are not familiar with nanomaterials, it's very simple. A nanoparticle, this is the range. A nanoparticles, this say a nanoparticles of 10 nanometer. If you compare it with a molecule of water, it's big a little bit than a molecule of water. The molecule of water is at the Armstrong level. So for a virus, some viruses, they can be at the micro range. Our red blood cells at the 5 micrometer range. A nanoparticle, it is smaller than your red blood cell. Look at the hair, it is at this range, 10 power minus 4 meter in diameter. A queen, you see, is 1 centimeter diameter. So as you can see, and even a watermelon hair, it's big here, if you take a case of a benzene molecule, 0.5 nanometer, which means what I want to show you here, it's if you are dealing with nano, you have to make sure that you are working, let's say between 1 nanometer to 100 nanometer. So here we are speaking about nanomaterials. If you go above that, you are dealing with the micro range, and micro range when it comes to nanofluids is not suitable because the particles will be very big, and due to the gravitational effects, maybe the efficiency of the heat transfer fluid itself, it can go down because of that reason. So a nanoparticle in a viscous medium like ethylene glycol or oil, it can be stable because of the viscosity of the system. and the distribution can be high, and that is what we are looking for. So selecting the material, again, let me just go back quickly. So selecting the material to create or to design your nanofluid, of course, you have to do research. Here, what I'm showing you, this figure here, it shows you the difference between conventional heat transfer fluids, which are used currently in the technology of solar thermal systems. If you can see, this is the thermal conductivity in watt per meter Kelvin here. Compare it, these are liquids or conventional heat transfer fluids, ethylene glycol, mineral oil, water, so on. Compare it to solid materials, liquids, they have lower thermal conductivity. That's the reason why we need to combine between these two to enhance the thermal conductivity and the thermophysical properties of the nanofluid itself. Measuring the thermal conductivity, we use this one-dimensional law or Fourier's law, which shows you that the thermal conductivity equals the heat which is applied and the distance between the plates over the area of the plate and the difference in temperatures. So this mechanism, it allows you to measure the thermal conductivity of each system, either solid or liquid. I will show you something about this in the next lecture, the next slides. Of course, I will talk about more about the heat transfer and the theory of heat transfer in my future lectures at the Virtual Learning University for students who are interested. So what are the challenges of nanofluids? Of course, particle concentration, you have to control. Particle selection, stability, particle size, flow rate. The viscosity can impact the flow rate, the cost, the pumping power. If you have high viscous medium, you will need a high cost pumping power, and you don't need that. So you have to take into account all of these to create a suitable, highly efficient nanofluid, which can be used in different solar thermal systems. So you will have high efficiency. Even you can reduce the area of the plant. You have lower pumping power and friction factor. So all of these things, they have to be taken into account in order to design a suitable heat transfer fluid or advanced heat transfer fluid, what we call nanofluid. So as a proof of concept, we have done this research here in South Africa. We use what we call a wet chemical synthesis approach. We're trying to create what we call silver nanoparticles and nanowires inside what we call ethylene glycol. Ethylene glycol is a heat transfer fluid, of course, as I showed you in the previous slide. What we found very beautiful results. As you can see from this figure, the base fluid or the ethylene glycol, it has lower thermal conductivity. This is what I was saying. By introducing nanoparticles, the thermal conductivity was increased nicely there. Here, what we are doing, we are changing the concentration of the particles. At different temperatures, we found that even at high temperature, which is 30 degrees only, I didn't go above because of the limitation of our systems. So what we found that by adding these nanoparticles, silver nanoparticles, the thermal conductivity was enhanced tremendously. Imagine with me now, if you are using heat transfer fluids in our plants in Morocco, and if we can add nanoparticles, just imagine how much power we'll harness. That's why we need really to create a human capacity, not only in Morocco, but in Africa and the Arab world. So our students and our newer generation can learn and can contribute to enhancing the efficiency of existing systems, or maybe building new systems. We have to be independent. The enhancement was almost 20%, and this is really huge. And this is, by the way, a publication that we managed to publish recently in 2018. You are more than welcome to go and read more about that. So recently, as I mentioned here, we use the wet chemical method. Now, we are trying to design other methods where lasers could be used. And I will share with you why we want to use lasers. So the system is this one. This is the configuration. This is the lab. I'm very proud working with African students. They show huge commitment, and I'm very thankful to them. Adibisi from Nigeria, and also Mpampo from South Africa. They really worked hard with me in this lab, and we managed to produce very beautiful samples or nano fluids. Different materials from silver, gold, aluminum, copper, molybdenum, graphite. The liquids we use it is ethylene glycol, water, synthetic oils. The laser parameters are there. The laser that we use is a UDMIAG or INDIAG laser, which operates at 1064 nanometer. The laser energy is 90 to 100, between 90 to 100 millijoule per pulse, because here we are using pulses. It's like bullets. We are not using a continuous laser. When you are at the lab, you will hear a noise, like you are bombarding with bullets with a gun. Ta, 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 ta. This is what you will hear. And that is the target there. This is a motor. You send your laser, you focus your laser, which is pulsed, and you do ablation of the target. So what we are doing is a one-step method. We produce the nanoparticles directly in the liquid. This is a beautiful method, and I will show you why we selected this method. Look at this curve with me. This, by the way, this curve, it comes from one of the leaders in the world, laser ablation in liquid, Professor Stefan Barkowski in Germany. And I'm lucky I will visit him next week. He invited me recently, and we would like to take this research to the next level. So what this professor mentioned in his publication, which appeared in 2017, through their research, we found that this is absolute cost, this is the nanoparticle mass. Remember, if you are pumping or ablating your material or target, you are producing nanoparticles, and nanoparticles, they have a mass. So that is the nanoparticle mass. That is the absolute cost. How much it will cost you? Because some people, they will say chemical methods are cheaper than using lasers. Of course, a laser, you can make an investment. You can buy a laser, it's expensive. But look with me here. If you are trying to create these nanofluids, if you are doing fundamental research, which means the nanoparticle mass, if it is low, of course, this orange color is chemical reduction or chemical methods. The cost is low, low, low. The laser, it's high, because here you are dealing with fundamental research at the laboratory. But now if you want to go to industrial, that is the threshold. You reach a mass where the lasers become much cheaper than what? Than chemical methods. Because with lasers, you have one laser and you do this ablation. You can do it till the laser it's gone. Maybe it will take you for more than 20 years, that laser. So the cost is really lower than chemical methods. Remember, chemical methods, if you make, I believe there are scientists today with us who know that chemical methods cannot give you pure nanoparticles. Remember, why the cost is high for chemicals? Because once you make your nanoparticles, you have to make sure that they are clean. Sometimes chemical methods, you add surfactants. With lasers, you don't need to do that. So and chemical methods, sometimes you use two steps. You create the nanoparticles and you mix them. So now if you want to create a company to produce these nanofluids, or if the government want to invest, they have to invest in a chemical laboratory or a nanoscience laboratory, and also to make nanoparticles and to mix them. So the process is huge and costly. With lasers, you don't need that. you produce the nanoparticles purely inside the heat transfer fluid nicely. If you are dealing with industrial level, the cost is lower. Again, lasers, recently, because there are huge development, the cost is going down of lasers. They were expensive, but the cost is going down. More power, but the cost is lower. So because there are researchers who are doing research on lasers, they managed to develop very beautiful lasers, small lasers. They can be purchased for universities in Morocco or even other countries in the Arab world or Africa. So they can be used nicely for research and also maybe for doing industrial and making maybe some agreement with other agencies to produce for them these kind of nanofluids. So I think this is, someone has to think about it seriously, particularly in Morocco, where we have huge plants that we need to produce our own nanofluids, so they can be used for as a heat transfer medium in our systems in Morocco, and we can be independent. And we can reduce also the cost of operation. So now, by using these lasers, we managed to produce copper nanoparticles, as you can see there in ethylene glycol. This is electron diffraction or selected area electron diffraction. It shows you clearly that we have solid particles of copper. The size distribution is very narrow. We have around 7 nanometer. With the chemical method, it's difficult to arrive to there. We tried the chemical method. We got something like 40 nanometer, and also the distribution, it was not narrow like this. With lasers, directly we got pure copper with 7 nanometer in ethylene glycol. Of course, the copper, it can be coated with an oxide layer, but very tiny oxide layer, because copper gets oxidized in general. But anyway, we tried this, and I will show you the result we came up with. So the silver, of course, we have tried copper and silver. Silver, it shows you that we have nanoparticles, crystalline nanoparticles. Can you see the planes there of the atomic planes? Are very nice, beautiful. Of course, the selected area diffraction, what we call the particle size distribution, of course, is narrow. We got something like 12 nanometer when it comes to. So again, I will move faster. So Prof. Nawi, the time, do I have more time, or I should maybe be fast?
You have around 10 minutes also, if it is enough to continue.
Yes, of course. I will make sure I will finish in that time. Thank you very much.
Good luck.
Yeah. So when it comes to laser ablation, the mechanisms, of course, this is what I'm showing you here. You have your target, as I was speaking about copper. So you have pulsed laser, you have the medium where you want to do your ablation. This laser, this pulse, it is highly energetic. It's a short pulse, highly energetic, will cause melting and evaporation of the metal. You create a plasma. So this plasma, because it's the temperature of the plasma, it's high. So a layer of the vapor of ethylene glycol will be created in a fast way. So because of high pressure inside this cavitation or small cavitation, the plasma will be shrinked. And as I mentioned before, plasma is a form of a gas of copper atoms. So these atoms will accumulate and they will create some kind of nucleus or nanoparticles, inside what we call the cavitation. And once this plasma is shrinking and disappeared, the formation of nanoparticles inside the cavitation will appear. And once this cavitation is done inside the liquid, the particles are released inside the liquid. This is the mechanism, and there is a paper, of course, we published it recently. You are more than welcome to go through. And of course, as I mentioned, the short pulse of the laser will come to the metal, it will melt it, and because this is highly energetic, this material will be evaporated and the plasma will be created with some shock waves. That's why you will hear some sounds when we are doing this kind of experiment, which is beautiful. So in our research, we do experimental, but of course we have to do some computational. So to study our systems, because this way it will help us to reduce the cost of research even. So we design our systems through theoretical studies before embarking on that research. So we created this system, which is ethylene glycol silver nanoparticles, and of course, ethylene glycol copper nanoparticles and ethylene glycol silver nanoparticles. We made these configurations with Atom SK and PACMOL. People who are dealing with computational, I believe they know more about this. So of course, you have to create a configuration to study the heat transfer and of course, the thermal conductivity. You do predictions of the thermal conductivity. So of course, to do this kind of calculations, molecular dynamic calculations, we use what we call large-scale atomic molecular massively parallel simulation, LAMPS. Of course, to do this kind of calculations, you have, can you see with me here, the molecules are moving there. You have to introduce some what we call potentials because these materials are interacting with each other. So now you have to know the energies of interaction. You have to introduce potentials. So this is the Lennard-Jones potential for the liquid. And this is the M potential, of course, or the embedded atomic model potential for the metallic or the copper atoms, which is there. So this, it has to be introduced while doing the calculations to make sure that the interaction between the atoms inside the system are confined. So of course, before carrying on the calculations of the thermal conductivity, we have to make sure our system, it has a solid nanoparticles and the liquid. By doing what we call the radial distribution function, we know that our nanoparticle or the designed nanoparticle, it has this behavior. If it has this sharp behavior like this, it shows you that it is a solid, and this is the radial distribution function, and this is what we call the radius from one atom inside the system surrounded by other atoms. So you do the radial distribution function and you will know exactly if it's a liquid or a solid. So by having this behavior, we know that it is a solid. For the liquid form, it shows clearly that the peaks are sharper near to the center of mass or the atoms that we are interested by. But if you have a liquid, the distribution will go to 1. And if it has this behavior, which means you know that you have a liquid. So now we know that we have a solid liquid configuration. We use it what we call, we calculated the thermal conductivity by using Green-Kibo equilibrium molecular dynamic method. The theory is very nice because it allows you to study the thermal or to predict the thermal conductivity via computational. So the Green-Kibo, it's the formula, it shows that the thermal conductivity equals the volume of what we call the system that I showed you, divided by the Boltzmann constant and the temperature and the integration of the heat flux. And the heat flux autocorrelation function is this curve that you are looking at here, because those particles that I showed you here, which are beautifully dense in Nicole, so when you introduce a force at the beginning, what happened? The particles, they move faster. So now before doing the integration, you have to wait for the system to be at equilibrium. That's why we call it Green-Kibo equilibrium molecular dynamic. Once the system at an equilibrium state, we do the integration and we get the thermal conductivity. Of course, the heat flux, it is this equation, and this one is the one which gives us this kind of heat flux autocorrelation function. It has what we call the kinetic energy, the potential energy, the enthalpy, the velocity of the molecules, and the forces between the atoms. You see, it is very simple and nice, and it helps you to predict the thermal conductivity. Of course, we do computational, but again, you do computational, you have to confirm it experimentally, otherwise it will not make sense. So we designed this system to see if our predictions are true. This system, they call it, what we call it, is a steady state system, hot plate steady state system. We have the 2 cylinders, the hot cylinder, the cold cylinder. You have your nanofluid between, you apply a power. So you apply a power, you heat this cylinder. So the heat will be transferred from this to that plate. By using this one-dimensional heat conduction equation, you will be able, because here you have, this is the heat which is generated by applying the power, equal the thermal conductivity, the area of the plate, divided by the distance between the plates, and the difference in temperature between the cold and the hot plate. And from there you can know, and this is the system at the lab, there you can know the thermal conductivity of your system. And we compared the computational results with what? With the experimental, and this is what we found. For example, the experimental data is the blue line, and the prediction, the molecular dynamic predictions are this line. As you can see, these are very beautiful results because they are confirming each other. This is for copper, and this is for what we call silver nanoparticle ethylene glycol. And both of them are showing that there is an agreement between the computational analysis and also the experimental. And by the way, the system, it was built at the lab, at the Tempa labs, and we are happy that we are using it currently to study our systems. For the efficiency, because this it was done while the ablation by LISA, it was only 5 minute time. See, but now we're trying to see what is the impact if we increase the time of ablation. What we found that also the efficiency is increasing due to the ablation time, because more ablation, more particles inside the system. So for it gives us a 30-minute ablation time. It gives us around 24 enhancement in percentage for copper. For silver, it gives us 30.16 enhancement in percentage, which is beautiful results. And the publications appeared this year. You are more than welcome to go and to read more about that. And now the ongoing research, what we developed in terms of selective absorber and nanofluid is tested now. We build this system, of course, and we are trying to test the systems that we are developing, and we are getting very beautiful results, and we are very happy. By the way, these are the team there that I'm working with. This is my wife, Touria. She's working with me. She's a Moroccan scientist, of course, and proud that she likes science, you know. And thank you very much.
Thank you very much, Dr. Saleh Khamlish, for this overview of your activities and your innovative research, and it's very promising, and it's in good agreement with the roadmap in Morocco in terms of thermal way of converting the solar. So thank you very much. I want just, if you allowed me to give some summary in Arabic for Arab word, which you always we did.
Shall I stop the sharing, Prof?
I think Salim, he will stop it again, I guess. Is
Yes,
it the case?
I'm going to stop it now and continue, Prof. Ahmed.
Okay, so
yes.
you see my slide, yeah?
It is there.
Okay, so as you know, I am the Ahmed Nawi. I am professor at the university before, and actually I am the سأتحدث باللغة العربية إذا سمحتم. أنا مؤسس جامعة التعلم الافتراضي، رئيس المجلس العلمي لمعهد بحوث الطاقة الشمسية والطاقة الجديدة في المغرب. يعني لست الرئيس بل الرئيس العلمي للمجموعة التي تفكر وتنصح المؤسسة. عضو في هيئة تحرير مجلة Solar Energy and Solar Cell، وسينيور ممبر في AEEE اللي هي معروفة عالميا. دكتور صالح خميش، أشكرك، وأنت باحث أول، يعني Principal Investigator ومحاضر جامعة جنوب إفريقيا، مؤسس مبادرة الطاقة النانوية نانو، هي يجب أن لا نتحدث نووية لأنها شيء آخر، من أجل التنمية المستدامة في إفريقيا. تحدثتم عن الآفاق الحالية والمستقبلية لتقنية النانو في أداء أنظمة الطاقة الشمسية الحرارية. نحن محظوظون في جامعة التعلم الافتراضي أن يكون لدينا 3 مناهج أكاديمية متكاملة تشكل وحدة أساسية في علوم المواد للطاقة والتخزين وكفاءة الطاقة. أنتم واحد من الذين سيدرسون كل ما هو يعني له علاقة بالطاقة النانونية والحرارة. هناك الأستاذ بن يوسف، هناك الأستاذ طالب من باريس، وهناك بعد الظهر اليوم الأستاذ طارق. طيب، الدكتور صالح خمليش باحث رئيسي كما قلت في تكنولوجيا النانو ومحاضر بجامعة جنوب إفريقيا وخبير في الأنظمة الحرارية الشمسية. سلط الضوء على موضوع متعلق بتقنية أو تكنولوجيا نانو في أداء الأنظمة الحرارية الشمسية بما في ذلك السوائل النانونية وقدرتها على نقل الحرارة بأكثر فعالية. أكثر من هذا، من الضروري تصنيع مواد مستقرة للغاية ودائمة في منظومة المرايا كتطوير مواد طلاء جديدة تكسب خصائص كيميائية وفيزيائية وميكانيكية عند تصغيرها للحجم النانو. هناك أيضا تطوير مواد طاردة للماء، هي أيضا في الموضوع تضم خصائص مثل سطح أوراق اللوتس. اللي البارحة كان هناك يعني فيديو في هذا المجال. طيب، أظن أن الطلبة اللي موجودين، وأتمنى أن يجي طلبة آخرون، يرون كيف يمكن أن نستعمل البحث العلمي في المختبر في مواد النانو ونوظفه في التكنولوجيا كما وصف السيد الدكتور خمليش. فالمغرب الآن يعني هو من أكبر الدول التي ستستعمل الحرارة what we call power concentrated power لتوليد الكهرباء. وبالتالي يعني في المستقبل هذا الموضوع يجب أن يجد مكانه في التعليم العالي والبحث العلمي. وعندنا في مؤسسة جامعة التعليم الافتراضي سيكون موضوعا مهما جدا. وعندنا كما قلت يعني مجموعة من الأساتذة الجامعيين منهم دكتور صالح خميس الذي سيعطوا هذه المواد، وحيكون يعني هناك باج ويب على في المستقبل اللي ممكن الطلبة يتسجلون في هذا السيلابوس أو هذا الموديول إلى آخره. وشكرا لكم وشكرا للسيد دكتور صالح، وأعطي الكلمة أو الفلور إلى السيد سالم.
شكرا بروفيسور أحمد، and شكرا أيضا to Professor Khamloush. The things it was really good. Now let's go to the questions and answer session and the comments from the attendees. And who wants to talk, please raise your hand there, or you can write the questions in the chat also. Starting with the first one, Professor Nuruddin. Yes, please, welcome. Yes, go ahead, Prof. Nuruddin.
Can you hear me?
Mm-hmm.
Yes.
Thank you, Dr. Salim. Thank you, Dr. Ahmed. Thank you very much, Dr. Saleh Khamlish, for your presentation and the quality of your information about nanomaterials. My question about you're talking about the nano fluid. Okay. Given that the temperature and the pressure inside tubular. Okay. What about the stability of a nanofluid? The stability is important parameter for nanomaterials, especially nanoparticles. Thank you, Dr. Khamlish.
Thank you very much, Professor Noraddin, for your important question. So when it comes to stability, again, I will go back and I will mention again that currently what is used is mainly is, let's say, oils or synthetic oils in the CSP technology. So now by adding nanoparticles, of course, sometimes due to agglomeration between the particles, you will have what we call, or interaction between the nanoparticles, you will have what we call agglomeration sometimes. And these particles, they can grow bigger. And due to the gravitational effects, we can have stability issue. I agree with you. But now, if I am using a laser and producing what we call plasmonic nanoparticles inside the system, or metallic nanoparticles in general, so what we have for the stability, we have what we call electrostatic stability. The particles are charged. They have same charges at the nano range. Imagine now you have two particles at the nano range. You know that the surface to volume ratio of a nanoparticle is very small, meaning that the atoms at the surface of the nanoparticles are highly active and they are electrostatically charged. If I have two particles, let's say of silver, which are charged positive, so they will not interact because they have we will have what we call electrostatic stability. They will push each other. They will not interact. They will interact only if they have different signs or different charges. So we have tested this and we got beautiful results from that. And even sometimes if the particles are not charged, we can create mechanisms to stabilize them and to make them to have what we call electrostatic stabilizations. Otherwise, you can use surfactants, which can help you to increase the stability. The issue of surfactants, mainly they are polymers. So now imagine you are working at 400 degrees. Of course, the polymer will have degradation and you will lose that property to stabilize your nanoparticles. That's an issue of chemical methods. So by using lasers, I believe we have what we call electrostatic stabilization. Hopefully I answered your question, Professor Noraddin.
Thank you, Prof. Comments from Mohammed Yusuf. Nice, he's saying a nice and interesting presentation. Thank you, Dr. Khamlish. Hajar Faris, thank you for this interesting lecture. Let's go for, yes, Professor Abdul Hafid Talib, please welcome. Comments?
Yes,
yes.
I open my mic. Okay.
Very good.
So first of all, I would like to thank Professor Khamlish for his kind presentation. Very interesting result he showed us today, and he shared with us many results developed in his group, and we're happy that he have a very huge scientific activity in South Africa. And yes, so my question today is dealing with the size of your nanoparticles. You mentioned that using this laser ablation in liquids technique, you are able to prepare nanoparticles. And what is about the control of the size distribution? As you know, the size distribution can influence the properties of maybe this nanofluid, and how you can control them using your method.
Yes, thank you very much, Professor Abdul Hafid Talib. It is very nice to hear from you. I'm very happy, really. And thank you very much for receiving us in France previously for the NanoSmart conference. It was really beautiful. We learned a lot there. So for your question, yes, you are right. Sometimes the particle size distribution, it can be a problem. But from my slides, if maybe can I go back to my slides if you allow me?
Yes.
Maybe
please.
just to, yeah, let me just go back quickly there. So what I'm gonna do, Char, I will just go back quickly. Okay. Okay. So I'm going to share again, if you allow me, to my screen.
Yeah.
So I will go down there to the particle size distribution that we got. Okay, so this is the slide. So if you look with me carefully here, it's I call it a narrow size distribution here. This is what we got. Of course, for the Cooper, we got between 3 nanometer and 12 nanometer. But even though 12 nanometer, it's still very small, and we didn't really observe some impact when we were calculating or measuring the thermal conductivity experimentally. And for the samples, I'm still studying them now. I have samples now sitting with me 2 years. And we do, from time to time, we take measurement of the C, SEM, TEM, and also what we call the UVVs. And really, we didn't see huge degradation of the system, even though that the distribution, it is like this for the Scopa. Even for the Silva, the same thing happening. And what is beautiful, we found that the electrostatic stabilization, it helped us to avoid agglomeration, you know, and it was fantastic. But we didn't observe this when we used chemical methods. Of course, chemical methods, they didn't allow us to have highly stable nanofluids. So by ELISA, we have narrow size distribution, and it's really helped us to avoid the problem of stability. But again, I cannot answer just 20 years, because I haven't done that yet. We are now, it's at the second year now studying our materials. So we are planning to do these studies for, let's say, at least 5 years from now, to see if it's true the stability will go for longer time. But currently, 2 years, and still the nanofluids we developed are still stable. So this is what I can say. But from the distribution, it shows, this is the distribution what we got. And hopefully I answered your question, Prof.
Yes. Thanks a lot. It's you answered my question. My second question, it's going to be dealing with the use of these nanoparticles in nanofluid. And as you mentioned, you will use them in dynamic system. I mean, maybe these nanoparticles can interact. Maybe you can have some collision between them in this system. Maybe this can be a source of agglomeration. Is it right?
Yes, yes, Prof. But again, when it comes to, let's say, the nano range, and if we have what we call electrostatic stabilization or charged nanoparticles, even if there are, let's say, if we, as you mentioned, collisions, but I don't believe at the nano range, if we have similar charges in the nanoparticles, they will really interact. I don't believe that, because remember, the velocity is not really very high when the liquid is moving. So this is what I can say, because they are charged similarly. So I don't think they will really interact. They will have what we call repulsive forces, even if the liquid is moving. And by the way, the problem of agglomeration in these systems, it can happen while the system, it's not moving. A moving system, because in my last slide, I showed you that we designed the CSP, a small scale CSP system, and we are trying to study these liquids. Interestingly, what we found that by moving these nanofluids, it's much better if we study them in a steady state system when we are doing the thermal conductivity. When we are doing the thermal conductivity in the steady state, we have this problem of sometimes particles, they may be sometimes with the temperature, they can interact, but mainly for metal oxides, but not for metals. But for metals in general, in the moving system, while they are charged, so you don't care about that problem because it's not really happening. But if the particles are not charged, or if they are at the micro range, I agree with you, you will face that problem.
Okay, thanks.
Thank you, Prof.
Thank you, Prof. Let's go for maybe in the same presentation also. Ahmed Hilal, yes, thank you. He is saying thank you for your nice talk concerning this synthesis of chromium-based absorbers. You used electronic evaporation. When scaling up, you maybe need a more cost-effective method to get cheaper absorber. Do you have an idea about a simple method to achieve large area absorber? Thank you. This is from Ahmed Hilal.
Thank you very much. Thank you very much, Professor Hilal, for your beautiful question. Actually, I showed a slide in my presentation which shows that system. Let me again share my slide again.
Yeah.
And yeah, so let me share it and I will show it again. Okay, this is the one. Let me go up. So yes, okay. So now, as I mentioned previously, to make this configuration with an electron beam evaporation, it can be costly. Of course, I agree with you 100%. But recently, I saw some people in Germany, what they do, they designed homemade systems to evaporate metals. And they introduce oxygen, a very simple system. You can make it even at the lab. And they inject oxygen and they can do the deposition while the tube is rotating. That can work. It can maybe have a little bit, the cost can be higher. But now, if you want to make, let's say, a porous system where light can be trapped, we can do etching of the surface. That's why I showed this slide. You see, if we have a reactor, if you can design a reactor, and if you can, of course, I didn't show the chemicals here because this study is just started now. I don't want to share more information about that. So the chemicals we use, we can put a tube, very big tube inside the system, and we can add heat and some chemicals, which those chemicals can etch the surface, and they can create for us pores or nanostructures where the light can be trapped. And imagine with me, you have one reactor or hydrothermal reactor, which is big like this. Maybe it can be even 2 meters long or even 1.5 meters long. We can design it. And we are working on that, of course. And always, if you have this system, you can just put your tube, stainless steel or a metal that you are interested by, you add your chemicals, you introduce temperature, and you do chemical etching of the surface. We tried that at a smaller scale and it worked beautifully. And we published recently some papers on that. If you are interested, I can share them with you. Please, my email, it's there and I can share or I can send you so you will know more about this kind of technology. And this is the best way if you want to start producing these receiver tubes in Morocco. I think that will be the best way. And I'm willing to take this technology to Morocco, if I'm allowed, of course. Thank you very much.
Thank you. Question from no name here. It's Galaxy A12. Okay. What are the main factors could possibly be considered as possible sources of amplification of the thermal properties, the nano fluid observed through the laboratory measurements? Is it clear, the question, Prof. Khanoush?
Okay, let me check here, stop sharing. So the question, it is on the, what are the main factors could possibly be considered as possible sources of amplification of the thermal property, the nano-fluid of, okay, again, I'm gonna share my slide again.
Okay.
Okay, these are the factors. Okay. So this is what I was trying to explain. So the particle concentration, for example, sometimes you have, if you are dealing with, let's say, noble metals, like let's say silver. Silver is very expensive. You cannot really add 1 of silver and 100 milliliter in glycol. It doesn't work like that. You have to put maybe, let's say, very, very low concentration. And we have done that, of course, 0.00 maybe gram and 1 milliliter. So there the cost is very low because the concentration is very low. So you have to take care about this. The particle concentration, the particle selection, of course, from the curve that I showed before, there are metals, they have different thermal conductivities. Sometimes you have to select a metal which have high thermal conductivity, like copper. That's why we are interested by copper. So that is one of the reasons. The stability, as it was asked before, the stability is an issue. And by using chemical methods, we found that having stability, we have to introduce surfactants. And we found that that's why we move it to lasers. We can get what we call charged nanoparticles, and the stability is very beautiful. And we are still doing that research, of course. We are still embarking on that. Remember, the laser ablation liquid is a new technique. It's not an old technique. So there is plenty of rooms where we can enhance and try to bring more techniques to enhance the stability more and to find out more knowledge about that technique. But now, the preliminary results show that by using a laser, stability is fine. The particle size is a parameter, of course, a parameter, because again, Professor Talib, he mentioned it now about the agglomeration, because sometimes if your nanoparticle agglomerate, the sizes will be big. Even if you have what we call Ostwald repinning process, where bigger particle absorb smaller one and grow, that's a problem because the particle will not be stable. They will have, and maybe you will have even clogging in the tube. They will block the tube, and you will have problems in your system. So that's, of course, is another one. The flow rate, the other stuff. So when we are talking about the enhancement of thermal conductivity, by doing computational analysis, we found that when the heat is absorbed, of course, absorbed by the metallic nanoparticles, the atoms are vibrating, and heat is vibration, temperature is vibration. So the vibration of the atoms of the metal, it causes, of course, the higher vibration of the molecule of the liquid, and the heat is transferred through this system by this mechanism. And this is what we are trying to do. We're trying to solve some Newton equations. Classical physics is not quantum here. We're trying to solve some Newton equations, second law of Newton, to find out how these vibrations can contribute to the heat transfer itself. And we found that really metallic nanoparticles, they absorb the heat and they have higher heat transfer, and they contribute to the layering effect. When you have a nanoparticles, these molecules, they come around the particle and they stack. They create a layer. And because the particle is vibrating, the vibration is moving through the liquid itself, you have better heat transfer. That's why I show it this here, this figure here. You see, so unfortunately, I didn't put the heat transfer, the heat flux auto-operation function of the ethylene glycol alone. This is for the full system with the nanoparticle. It shows clearly that when we compare this with the nanoparticles, so the one with only the liquid, we found that the vibration when it comes to our nanofluid are higher in the system. And the heat transfer, it's much better, and the thermal conductivity, it's much better. So this is actually what is happening when we are dealing, or when we are speaking about thermal conductivity enhancement. And hopefully I answered your question, Prof.
Hopes, inshallah. Any comments? He can mention it, please, in the chat. Any other questions or comments, please?
I think Tarek, he asked. Tarek.
There is Mr. Hassan, Dr. Hassan Ahmoum. Yes, please. Please open your mic, please.
Okay, now it works.
Okay.
Sorry. Oh, okay. Thank you, Professor Khamlish, for your presentation. I have one question regarding multi-layers. When you show CrO2 and another layer Cr and another layer CrO2, right? Can you please come back to that slide?
Okay.
Okay, I'm interested very well on okay, when you shed light on your film, then you start to measure the temperature as a function of time.
This one. Are you speaking about this one?
No, just a substrate multi-layers.
This one
with multi-layers. Yeah. Yes, can you show that figure that you have temperature as a function of time?
Okay.
No, not this one. Not this one. Yes, this one.
This is the temperature versus time. Temperature versus time.
Yes. No, I want the figure. Okay, this one. Stay here.
Yeah.
Yes. So I see you present here only the metal substrate SS and only CrO3, CrO3, right?
Exactly.
So my question is just I want to know the behavior of CrO2O3 alone. You understand what I mean?
No, I understand. You know, when we are, yeah, continue, please.
Especially I want to know the slope, la tangente, which one is higher, which one is low, compared for multi-layer and one layer. So this is what I want to know.
Okay, if may I understand your question, are you asking that if I do this analysis only for the system without the stainless steel? So this is your question?
No, without Cr, just CrO2O3, just the electric alone.
Okay, only CR2 only alone.
Yeah.
Okay. So let me explain something here. We have done this kind of stuff before, but remember, when you are dealing with a dielectric, metallic dielectric configuration, here you are playing with what we call interference phenomena. So the chromium oxide is, of course, it absorbs. We have done some studies on that. It absorbs at the visible region, particularly if it is dark. If you manage to deposit it and it is darker because it has a green color. But now there are techniques that you can make it darker by heating it in a furnace. Now, if you use it alone in that configuration, you will have what we call high emissivity. It will absorb even at the IR region. This is what we found. And when we have done this, we didn't find higher temperatures. It was very low by using it alone. That's why scientists, they suggested that by dealing with dielectric materials, you have to go for a multi-layered structure where you introduce a layer between a metallic layer. Why introducing that metallic layer? Because this one, as I mentioned, is a very thin layer. It allows the light to go out. It allows the light to be absorbed, and the portion of the IR also, it is moving through the material and it goes to the metallic layer. The metallic layer will help you to reduce the emissivity because it helps you to reflect more the IR. And the portion of the light which passes again through the metallic layer and it comes here, it will be again, it will help to enhance even the absorption. But the IR region, it was reflected by this one. The rest of the light is again absorbed and converted to heat. But by using one layer, you will have high emissivity because one layer, it will absorb highly at the IR. So this is what we found, and there is a paper published on that. If you are interested, please contact me via my email and I will send it to you to show you why we didn't use only chromium oxide.
Okay, thank you.
Your micro, please.
Okay. My micro, it's off, sorry. Professor Tariq, you want to talk? Please go ahead.
Yeah, thank you very much, Sikhamlish, for your very interesting talk. So we carry out somehow some research, some similar research activities in our lab by trying to produce some nano additives for lubricating the wind turbines under some very, severe conditions, like similar to desertic condition, for example. And of course, as you mentioned, so we successfully managed to produce very interesting results at the lab scale using various chemical methods for producing this MOS2 nanoparticles based. And why MOS2? Because it has not only this this possibility to be reduced as in the scale of nanoparticles, but also it has this very interesting morphological and the structure, and which can help very much lubricating the system as a nano additives. So this is my question, because we according to the experience, our experience in this field, we found that it is interesting to control not only the shape, but also the morphology, because because we mainly use this solvothermal and hydrothermal procedures, and this is very sensitive to the operating condition, because if you suddenly don't control the temperature and the pressure, you will move from, for example, from nanoparticles to nanotubes shape, and this is also may impact the performances of our system, our formulation, not only in terms of stability, but also when we wanted also to scale up the process. And also another issue, it is important. So I wanted just to when you showed the slide using the design, the solvothermal reactor. So we did the same thing also in our lab, and also we have to pay attention to the safety issue, because sometimes under some operating condition we may have some surprises with respect to sometimes the reaction can go out of the control. So this is very important. Once the safety issue, that means we need to control the thermodynamics parameters, and do you have some experience in this kind of your system? For example, the reactor you design at your lab. So did you study the operating conditions with respect to the safety issue?
Yes, thank you very much, Professor Tariq Shafiq. This is beautiful to hear that your laboratory is embarking in this kind of research where producing nanomaterials by hydrothermal technique. So in our research, actually, what we do when we are working with the hydrothermal reactor, we don't really work at high temperatures. We work below 200. Because the materials we are using, it's not necessary really to go for very high temperatures. We just work below 200 to produce, if we are producing, let's say, or etching, whatever, producing.
Yeah, but
had an accident before.
Yeah, but although we fix the temperature at 200, yes, of the oven, but sometimes with the intrinsic thermodynamics reaction at the inside the reactor, sometimes the temperature can go out of the control and exceed this fixed temperature.
Yes, actually, we had an accident before. A student, he was reckless and he didn't follow the pressure gauge. He put his reactor and he went for lunch and he took his time. And the reactor exploded in the lab.
Yeah.
You know, so now we are making sure that the safety measures are followed. So the pressure gauge, the student mustn't move from the lab. If there is anything, or if the pressure goes high, he has to stop everything immediately and call us to find out what's going on. Because some students, sometimes they can really make mistakes. Even us, sometimes we can make mistakes. But these things are really not easy. We have to be careful, and I agree with you 100%. Using hydrothermal techniques where the temperature and pressure, they go high, they can cause some disasters.
Sure.
But now I can show that our system, we put even sensors recently, pressure sensors. We developed them even with open access systems. So even if the system reach a state where the pressure is high, it can stop automatically by itself. We have introduced this, and we are still developing it further. Because as I mentioned before, it's difficult for us to buy highly sophisticated systems. We just work with engineers and we try our best to reduce the risk. But the risk sometimes is there.
It's there, yeah.
So,
I have one student now, because of the issue is important. So I have one student now, his PhD thesis topic is devoted to the modeling of the safety issue of this reactor, or operating this kind of reactor. So maybe we can discuss afterwards the obtainment. Yeah, and also I have, if you may, I have also another question, because I was also very interested in the slide you mentioned the importance of when you show the techno-economical investigation, and you saw that using the laser sometimes it can be in terms of economics, it can be it can beat the chemical process and become in terms of investment return it's become very interesting. So this is also a very important point. If you want, please, you can give us more details about this issue, because we are also interested in this kind of techno-economical investigations.
Prof, thank you very much for this, and I'm open for collaborations. I am open to jump to Morocco and to visit your lab and other professor laboratories, and I'm open to work with you.
Thank you very much. Thank you. Welcome.
That is a dream, by the way. That's my dream, is to contribute to the development of Morocco and the Arab world. And I will be grateful, Prof.
Yeah.
You know, to
so
jump
please,
and to
Yeah, please, Saleh, if you can show the slide and give us some more information about this. I mean, this modeling, this economical modeling, because it is not very easy to do this kind of things. We need to consider a lot of parameters.
So,
not this one.
Let me just go back a little bit. Not here, maybe, I think.
With the German, not this one, because this shows slide. Yes, this one.
Yes.
Yes, this is very interesting, I found.
Yeah. So here, the group of this professor, Stefan, they carried on a study. Actually, these people are specialized in lasers. And they carry on, and these people, they work on the scaling up process of producing nanofluids in general. That is their interest.
Yes.
So through their research, they found the compound between the two, the chemical and the laser ones. So now when you reach a mass, a critical mass, there is a threshold where there is a shift, and chemical methods, they become much expensive for the simple reason, because the chemical methods, you need to follow up with other processes for purification and for other things. And you use different chemicals, you use different things that they can impact the cost and the everyday. But at a lower mass, for a laboratory research, chemical methods, they can be fine. They can be fine. But again, I don't believe that Morocco, I believe that there are researchers like Professor Saqqad and Maser. He has lasers there. I'm not sure. I'm going to visit him if I go to Morocco this year or next year. They have lasers. I want to find out if they have pulsed lasers. Why not having collaborations with them and trying to investigate this?
Okay.
Because that is fantastic. And to buy a laser, I don't believe it's very expensive.
Yeah.
Because buying one laser, it can work for different institutions. Maybe we have one laser at Maser or Green Energy Park or whatever. So researchers, they can come there and they can use and produce materials and try to understand, to find out how they can contribute to producing nanofluids through lasers. Lasers are the future, by the way. And I hope that the Moroccan government will embark in this research where lasers could be used, because these German people, they show it clearly that lasers for the upscaling are better than chemical methods. And the reason is very clear. Yeah, thank you, Prof.
Okay, thank you, Salah. Very good.
You, Prof.
Thank you, Prof. All right. Prof. Ahmed, can we go for the video or you want to conclude our first session before going to the second?
Thank you, Ustad Saleh. I just want to thank Dr. Saleh, but I have one question before. Huh?
Okay.
Welcome, Prof.
Yes, the laser ablation is a very elegant method, very clean, although you say there are some safety to take care of. Have you made any startup with your know-how in this method in Africa to prepare different material and to sell it like via internet to gain some money or something like this? Do you have done this? Or I mean, the questions behind is your know-how is really very specific, that you can do something very special. Nobody is able, even Chinese or whatever, to do the same.
Yes, Prof. That is the reason of my visit to Prof. Stefan Laboratory in Germany, Duisburg University of Technology, because these people, they are working on the upscaling. In Africa here, it's difficult to raise the money to buy a laser. It's really not easy at all. Particularly, I am a foreigner here in South Africa, so it's not easy for me to raise the money for. I use laboratories of other professors. I go and I visit like what we call Swan University, or I go to UCT or Stellenbosch University. I use their facilities there. I don't have my own laser, but I use the facilities there.
I get
so
it.
now with these Germans, they contacted me recently and they were interested by this technology for solar systems, solar thermal systems. Okay. And they would like to work with us and to assist us in bringing this technology to Africa. And I hope that this technology will go to Morocco and other Arab worlds in the future.
Okay, thank you. So thank you for this talk.
Thank you, Prof.
It's very interesting. It shows the link between the lab scale and the application, and I think we are looking forward to see you in the virtual learning university to follow your course. I think students from Morocco also can learn a lot. I hope you can have some touch to Mazen. Mazen is the big guys responsible of CSP in Morocco, Noor and all this stuff, in order that you can sometime go and give talks also, or they have to follow our virtual learning university.
Exactly, Prof. Exactly.
So, I think So I will give the floor to.
Thank you, Professor Ahmed, and thank you, Professor Saleh Khamlish, for your excellent presentation. And excited. Before going to the second lecture, let me share you the video. Okay. Hope the sound is okay also.
Je voudrais souhaiter à toutes les honorables personnalités ainsi qu'à tous les participants la très cordiale bienvenue sur notre campus.
La deuxième édition du Green Africa Innovation Booster est le fruit de cette excellente collaboration.
Pour ma part, je représente le Royaume du Maroc en Côte d'Ivoire. J'aimerais souligner encore une fois l'excellence des relations entre mon pays et ce beau pays dans lequel nous sommes, grâce à la fraternité, l'amitié.
Pour le moment, enfin, on se lève de configurer la proposition des matériels, la propagation, le vous voyez la solidité et le processus de pouvoir atteindre notre
Après un an d'exercice de chaque startup, on essaie de sortir 15 meilleurs sur les 250 dans un processus d'évaluation que nous avons mis en place qui est propre à nous.
Et au Maroc, il était interdit de fabriquer des voitures de plus de 110 chevaux. Je crois que c'est qui a imaginé cette histoire-là. Vous savez, les politiciens, il faut qu'ils travaillent, donc il faut qu'ils inventent des lois. Et des fois, ces lois-là sont contraires à ce qu'on aimerait, nous,
Nous nous retrouvons ici en cette fin d'après-midi pour célébrer l'excellence à travers cette cérémonie de remise de prix. Il faut le dire, 60 compétiteurs venus de la Côte d'Ivoire et d'autres pays d'Afrique, notamment le Maroc, la Guinée, et j'en passe, eh bien, ont eu à présenter leur expérience de connaissance devant un jury présent ici parmi nous. Mesdames, Messieurs, nous allons vous permettre, eh bien, pour avoir quelques mots de cette compétition et comment cela s'est passé, nous allons recevoir ici Monsieur le Président de jury par intérim, Monsieur François Bourzex.
Alors, donc, le jury s'est réuni suite aux 3 séances d'évaluation qui ont été réalisées. On a vu beaucoup de très beaux projets et la sélection a été difficile à faire. Il y a eu des projets de nombreux pays, le Maroc, la Côte d'Ivoire bien sûr, et puis le Sénégal, le Nigeria. Alors, aujourd'hui, donc, il y a 4 prix qui vont être décernés, 3 prix à des startups et puis un prix d'innovation et de recherche. Et le jury a aussi décidé, j'en parlerai à la fin, d'attribuer 2 coups de cœur à des projets qui nous ont touchés et qui n'étaient pas classés parmi les excellents. Et monsieur Sako Mohamed Oïda, professeur à l'INPHB. Voilà. Et moi-même, François Bozek de la Fondation Moissia.
Et mesdames et messieurs, si nous avons aujourd'hui 2 prix spéciaux, c'est parce que ce concours a été très rude et très serré, au dire de nos différents membres du jury.
Chers collègues enseignants, chercheurs du Côte d'Ivoire, du Maroc, chers étudiants, chers lauréats, monsieur le directeur général de l'INPHB, je voudrais vous dire combien je suis heureuse d'être parmi vous. Merci d'avoir insisté pour que je sois là, monsieur le directeur général. Merci beaucoup. Et pourquoi je dis que je suis heureuse? Parce que l'Afrique est en train de nous montrer qu'elle peut se prendre en charge.
Okay. Thank you for listening. Please, Professor Ahmed, if you explain about
yes,
this video,
yes,
at least
sure.
for
Sure.
Go ahead, please.
Sure. This is a video from 2018. It shows the activity of Moroccan institution in Africa. This was the one of the video which show a cooperation between La Côte d'Ivoire, the coast, the Ivory Coast, and Morocco. And it was Erizan. Erizan is the Moroccan Institute for Solar Energy and New Energy. We built up, or they built up, the Erizan, a solar test facilities where there are panel or different solar technologies to be tested for capacity building for the student from universities, for capacity building for technician, etc. And it was this day, I don't remember which day exactly from the screen, but it's 2018, where a memorandum of understanding was signed between Erizan and the Côte d'Ivoire university there, and also the whole, since the official politics were there. Then they followed by some prize, I think 5 prize for a small startup. There are some student or small companies or technicians, they make some new innovation and they make a startup which is related to solar energy, and they got a prize. So it's a big day. It was a big day which show how important the cooperation between Morocco and Africa in general. So this, of course, this kind of cooperation is continue now, and we wish to have it. Erizan, Morocco wish to have it with other countries, and I think it's possible to have this kind of South-South dialogue in the future, which bring a lot in terms of sustainable development. So that's it.
Thank you, Prof. Ahmed. I think now related to the other questions, we will answer it later on, and we will send it to Prof. Saleh Khamlish, inshallah, and you can be in touch. I think now, Prof. Ahmed, if we can move to the second session.
I think the second station has to start at 2 o'clock Moroccan time.
Yeah.
What time is it?
Now it's 3. I have one of the videos related to the students, how it is moving with their activities, how Erizon, they really did a great job, and also related to the competition between the countries, the youth from all the countries. Let me share that one, please. Right, let me now back and share this video. It's about Best of Solar Decathlon Africa 2019. So let's share it.
In Africa, we know it would be difficult, but this is the spirit of the competition. This is the spirit of the challenge. Warm welcome to Morocco. Thank you very much. And we will start right now.
بالشعر الله الوطن الملك.
Yes. Yes, please, Prof. Ahmed. Any
Okay,
comments?
we still have okay, this is solar decathlon, which was in Morocco, and there are some prize for the best innovation, for the best technology, etc. I think many people know this. We still have some time, so I will show you some more stuff here, if you allowed me.
Yes, please.
I hope that I can succeed to do such. I try to play with my PowerPoint. So do you see it?
Yes, it is there.
Okay.
Go ahead.
Okay.
The sound or it is not coming.
You don't hear the sound?
No.
Yes, yeah. That's another problem. Yeah.
No. Only click on this escape within the same video. Click escape and then do the share.
Okay. Yeah. So you want me to quit and then to do it, or what?
Yes.
Okay.
And go for the video. Open it and do
video.
And click.
So open the video.
Yes, and escape.
Okay.
Click escape. You'll find that the window it will reduce.
So I have to share now, or what?
Now you can share. Yes.
Okay. So it's not working.
No.
There are some problem.
Okay.
So what about now?
Still
Do you hear?
No, nothing there.
And now? What about now?
Yes. Okay.
So that's, do you hear me?
Yes.
Okay. So that's one of the project in this solar decathlon what I have reviewed as a jury. It's a Bosphorus. It's from Turkey, and as you read maybe during the video, they have implement a lot of issue on sustainable development, even algae for water to take out pollution from water. There are many. It was very interesting, and during the jury, it was the first project in terms of innovation. Of course, during the decathlon, there are many issues. There are many jury. I was in a jury for innovation. There are jury for technique. There are jury for the best use of PV technology, etc. And every group they have to win in every jury, and at the end, the one he win more in different issue will gain at the end. But you have seen during the first video that most all groups they have win somehow, either in innovation or technology, etc. So you have seen, I think, except one they don't take anything. They have win something, and so everybody was happy at the end of the day. So that's it.
That's good.
So yeah. Okay. Unfortunately, we still have time for the.
I think we can have a break time now within 20 minutes, so we can come back.
Or we can make questions in discussion.
Also, it is possible. There is who's asking here. Let me check. Let's see how many countries are connected to this lecture. USA, Germany, Morocco, Bahrain, South Africa. Add the addition who's with us now, he can write his country also. Morocco, good. So we have USA, Germany, Morocco, Bahrain, South Africa. Who's else with us? You can write, mashallah, good. And let's see is it to the experimental? It was the previous question. So please, if you have any comments or you want to share your ideas also, it is open. We can discuss together. We have time before starting with the coming session now of the coming lecture.
We are getting more countries. We have Turkey, we have Algeria.
Now Algeria is coming there also. Turkey, yes.
You're welcome. Welcome our friend from Algeria.
MashaAllah, MashaAllah. Welcome all, welcome all. Really, we have a lot to do. Now just we started on the 16th of October within the opening lectures. Today is the 4th day, and we are continuing up to 30th of this month. Within, inshallah, a lot of information in different fields, and we are really looking for the development in all our Arab countries, in Africa, and Eastern now here. So we will see a lot of things. Professor Hussein, you can share. Yes, please go ahead.
There is something that Dr. Nawi said, that collaboration between Morocco and Sub-Saharan Africa is collaboration South-South. That's more a French term. I like to see it as North-South, because we are North Africa and they are West and South Africa. So when you say South-South, it's south of France.
Yeah, I know. But the people tell about us that we belong to South, and we love to belong to South anyway. But
well, it's Africa,
yeah,
so we are North of Africa.
Yeah, it's sure.
It depends on the geographical position, because if we are considering also North European country, then France become from the south. France and Spain and etc. They consider them as a southern countries. So actually, it is just a relative, you know.
Yeah. Who wants to share else? It's open. Any other questions, comments? Yep. Or I can. Yes, please go ahead, Professor.
So
Ahmed.
if someone wants to add something in the audience, it is an interactive discussion, and everybody can talk and say what he think about what all of the conference we had. If we have to improve something, he can do it. If we have some professor from Morocco, and I think we don't see anyone until now which are not member. Even some members are not there, so please be welcome. And if you have some questions, if you have some remark, student also, if you have remark, if you have any requests, please go ahead, and we are open to discuss. Dr. Hussein Ketani, if you want to add something about or to say something about the future, how to improve things, please go ahead. I think it's good to discuss. Sometimes we have to make this virtual learning or virtual discussion active and see what will bring.
Well, it's great that we see the agenda now on the website, so people can plan ahead. Sometimes the problem that people don't attend because there is talk about material science, and that's not part of their area. It's a nice something to watch, like yesterday, all this coating. It's very interesting how to make things and not through nanotechnology to make it water resistant. But many people who are doing research in different area, they may not be interested in seeing the whole science behind that. So so since it's broad, that's why we see some of the founding directors do not participate. And but and then there are other issues of timing, if you which part of the world you are, or if but having this online thing makes it easier to connect and participate. You don't have to travel. You don't have to be physically there, and you can connect from your hotel or anywhere, even if you're on travel or somewhere else. But having the schedule and sharing it with others, with whatever listservs or contacts, makes people plan ahead. They may just want to attend one lecture, or either a person that they know or a research topic that they really understand or work on. So
Yes.
I'm glad to see that there's that the schedule is there and it's shared with. I did share it with my contacts.
Yep. Was comments from Ahmed Hilal. He's saying that 19th and 20 October are off in Morocco. That's why people are absent. So this is his comment. Just we want to let you know that the YouTube also for the virtual learning university, it is starting today. So we are going. You can go over it, and you will see from the starting the first lecture on 16th of October. Just you can. I will share the link here. You can go over it also. And related to the website, also it is there. You can go and check related the lectures and other information. We are updating all information. Let me check to share the website first here, if you can see it. Yes, it is there. So once you enter, only write VLU platform.net, you will reach to the website. Is it clear there? You will have the founder of the VLU, and then this is a speech and my first experience with the remote teaching. And then you will find the lectures that we started from 16th up to yesterday. This is the milestone. You will have our roadmap, teaching objectives and methods, training tools and supporting materials that we are moving ahead with it, and how it is going to be for the evaluation of knowledge and registration. You will find the programs, renewable and environment science and techniques. This is the first section, and we have the second section, which is about the environmental policy, energy, and community development, and the sessions that we are having in the opening and the startup phase. The partners, we have the strategic partners, Arizona, Sabaik, and Manara, and we have other partners also, as you are seeing here. We have all of them. So you can move ahead and can have a read about these information, and others coming soon. We are updating the website. Then here you can see, meet the experts and all the staff. You will find them here, and you can contact the professors in different fields within their channels. And this is also, it will be our channels in the Facebook, Twitter, and Instagram. In the Instagram also, you can follow us there. That is already done, and you will find the others. The YouTube, it is ready also. You can follow it, and the LinkedIn also. Related to the About Us, you will find here the Virtual Learning University at a glance, message from the founder, board of director, also the advisory board and the transition committee, and the lectures also. Okay, just a minute, let me.
Could you close his micro to this guy?
I will close it now. Okay, now it's closed. We can see the lectures also. Let me go there. So this is the lectures in day one. All the lectures up, and also the speakers and the information about them. So you found them all here. Up today, day 4, and day 6, and 7, and we are moving on, putting each one their information, updating all the information for the, and we are having the milestones also. This is in the front page, and here you can go for it, and within the programs. So this is now it's in English, but it will be also in Arabic, the second phase. So this is about the website. Let's relate it to the link of the YouTube. Let me bring it here. YouTube. Day 1, day 4, and let's see the YouTube here. Okay. I put the link in the chat. You can see it all. This is the link. You have it there. And from my side, I open it also. And let me share it so that all of you can see it also. I will do share now. Let me check. Is it there or not? Yes. This is the YouTube. Once you write day 1 Virtual Learning University online, the opening, so that you will find all the days we are going to start, and we are going to put them there. So this is now for day 1, as you can go ahead with it. So who didn't got the time to join us in the starting, you can.
بسم الله الرحمن الرحيم. الحمد لله رب العالمين، والصلاة والسلام على أشرف الأنبياء والمرسلين سيدنا محمد وعلى آله وصحبه وسلم. الشركاء والزملاء الأعزاء، ضيوفنا وإخوتنا الحضور الكرام، السلام عليكم ورحمة الله وبركاته. معكم سالم رجب زايد، المدير التنفيذي لمركز سبائك للتعليم والتدريب عريق الحفل، ويسرني باسم المؤسس والرئيس التنفيذي وأعضاء مجلس إدارة جامعة التعلم الافتراضي أن أرحب بكم في اليوم الأول من المحاضرات الافتتاحية عبر الإنترنت لجامعة التعلم الافتراضي للسنة الأكاديمية 2021-2022، والتي ستستمر إلى تاريخ 30 أكتوبر 2021، وذلك للتعريف بالمناهج والقضايا التربوية والبرامج والدورات التي سيتم تقديمها من قبل المحاضرين من الأساتذة والعلماء والمختصين لجامعة التعلم الافتراضي، ضمن تآزر بين قسمي الجامعة. الأول قسم الطاقة المتجددة والبيئة والعلوم والتقنيات، والثاني قسم السياسة البيئية والطاقة وتنمية المجتمع، وذلك في سبيل تحقيق أهداف الجامعة في بناء المجموعات الدافعة والأفراد والمؤسسات لاتخاذ الإجراءات
الإيجابية والفعالة تجاه القضايا البيئية والعمل على تنمية المجتمع. ويطيب لنا بجامعة التعلم الافتراضي أن نعرب لكم عن خالص تقديرنا على اهتمامكم وتواصلكم وحضوركم لهذا اللقاء، كما يسعدنا تفاعلكم ومشاركتنا آرائكم ومقترحاتكم. والآن أدعو البروفيسور أحمد الناوي مؤسس جامعة التعلم الافتراضي رئيس المجلس العلمي لمعهد البحوث الطاقة الشمسية والطاقات الجديدة لإلقاء كلمته. وفقنا الله وإياكم لما فيه الخير والتوفيق والبركات، والسلام عليكم ورحمة الله وبركاته. تفضل بروف أحمد.
بسم الله الرحمن الرحيم. السيد الأستاذ سالم، أشكركم جزيل الشكر على هذه المقدمة، وباسمي وباسم كل الأساتذة المشاركين أريد أن أرحب بكم الحضور الافتراضي. وقبل أن أعطي الكلمة من جديد للسيد سالم الذي سيقدم الأعضاء الآخرين، أريد أن أعطي نبذة ولو صغيرة عن الجامعة الافتراضية، وبعد ذلك هيا نشرح في المحاضرات. فاسمحوا لي بعض الدقائق أن أعطي بعض الأشياء اللي لازم تشوفوها على الشاشة. طيب، أشكركم من جديد. فنبدأ أو لمحة عن الجامعة الافتراضية. ستكون منصات، ليس منصة واحدة بل منصات تعليمية افتراضية تحقق تكامل التكنولوجيا في المجال التعليمي باستخدام أدوات تكنولوجيا جديدة لتعزيز عملية التعلم والعلاقة بين المدرب والمتدرب. نريد بناء الموارد البشرية الدافعة لاتخاذ إجراءات بشأن قضايا البيئة والتنمية المستدامة. باسمي وباسم كل الأساتذة لأنهم كلهم مشاركون، هناك قسمين: قسم
That's good. This is just a brief about the YouTube that you can go ahead about it, because mashallah it was the first day around 7 hours. So you will have a time just to go over it and share the knowledge also. Prof. Ahmed, I think we can move to the second session or the second lecture with Dr. Tariq. Let's start now, 5 minutes before. And thank you for all of you that you participate with us today. And inshallah, we'll meet tomorrow, inshallah. We will give the more information related to the coming lectures, inshallah. All the best and have a nice time. Prof. Ahmed, your mic it is closed.
Yes.
Yes.
So I just, because I have a lot of open file here and I have to find out the one which is related to start. Yes.
Inshallah.
Okay. So now I find it. So I will share my screen and then I go ahead to present Professor Tariq. So do you see my screen? Yes?
Yes.
Okay. So we have now Professor Tariq. He's a professor of chemistry at the University Abdel Malik Al-Saadi in Tangier. This is in the boundary with Spain, and he will talk about toward harnessing local resources in sustainable development technology. I think Tariq Shafiq holds his PhD in catalysis, in catalytic process engineering from the University of Lyon in France in 1993. He was a postdoc researcher at the University of Patras in Greece in 1994. Then he worked at combustion division at NIRA and AIST in Japan, in Tsukuba in Japan from 95 to 97. Afterward, he was awarded as Fulbright visiting researcher at the University of California in Berkeley with Professor Bell. He is currently full professor, research director, and master course coordinator at Faculty of Science and Technology or Technique of Tangier, Morocco. His research is focused on sustainable development technology. I know him from the project of Erizen, where he won successfully a project, and he's working on different. For example, he talked during the discussion with Dr. Saleh Khamlish about his activity in terms of some nano liquid as lubricant for wind turbine or wind engine, etc. And I think he is very, very well known that he's trying to use local resources for sustainable development technology. I'm not going to take him too much, so I want to thank him first for being committed to give this talk and to be with us as a member of the Virtual Learning University. He will give a course where he will explain to you during his talk how he wants to do this, when, etc. So, Professor Tariq, the floor is yours. Thank you.
Okay, thank you, Dr. Nawi. I will try to share my screen.
Yes, go ahead.
So, is the screen is fine? All is okay? I can start.
Yeah, but you have to make your video also open.
To leave.
No, you have to make your video before you yeah.
Okay. Yeah. So
Yes,
I don't know, because I am actually, as it was mentioned, we are in vacation and I am connecting from my home. So if the connection sometimes is going wrong, so please forgive me.
Yeah. Professor Tariq, if you your camera decrease it, take it down, so that you, we can little bit.
Can see you completely.
Yeah.
Just move your computer a little bit down or whatever.
Yeah.
Okay.
So you close your video again.
We'll try.
Okay.
Now is okay?
Now we don't see you.
Oh, you don't see me?
No.
Okay.
Yeah, just open your video, that's it. Yeah, now we see you. If you accommodate your camera a little by moving your computer or whatever, or you
yes, let me see how I
it's
can
fine
do
now,
this.
but it's a
Yes.
little bit, just a little bit.
Yeah. So
It's
I will
mechanical.
try.
You have to do it mechanically, not with
Yes.
with electronic.
Is it okay now?
Yes,
Yes.
now perfect, perfect.
Okay. Yeah, because I don't see my face in the.
You don't
yeah,
need.
maybe
You don't need.
I have to do it like this.
It's fine. Go ahead.
Yeah. 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 Now it's okay.
Yes.
Yeah. So thank you very much, Professor Ahmed Nawi, for your kind words and for the introduction, and also for the effort you made to try this opportunity for you make use of virtual learning university, because this initiative actually has been also initiated due to the context of COVID. So we experienced this with our students, and we tried to make use of this technology in order to not stop communicating with the students and not stop exchanging the knowledge, which is our basic mission, as a university professor. So actually, my talk today is also connected to this concern of how we can make use of laboratory research activity in order to try to, through research activity, try to create some added value, and why not some economical activity through research activity at the university. So this is the strategy of our laboratory, is how to make use of chemical engineering tools in order to give a valorization to local resources in this context of the so-called sustainable development. So when we are talking about sustainable development, that means we have to create some added economical value, and also how to make use of these resources and energy in a sustainable way. So that means energy should be as much as we can renewable, and also we have also to consider the use of available resources, because this is very important. So with respect to this regard, so we settled down since the 2005 when I created this laboratory at my university, because we tried to gather a critical mass of researchers, of human resources, and try to make them working together on several research topics. So we are in our laboratory carrying out several activities, basically related to the energy field, but also to the environmental protection, the treatment of water, treatment of air pollution, and of course the use of nanomaterials and the local resources. So we are having 10 permanent members in our laboratory, and postdoc researchers, and basically we are also having some mostly 25 PhD thesis students. So 15 of them already presented their results, and also we get this PhD student not only from the local masters, but also from all the universities in Morocco, including sometimes some foreigners. We are, because also since we are a public university, we are also hosting a lot of African students, and for free, and they are participating and taking courses at our university. So this is what we so-called previously the South-South cooperation and knowledge exchange. So as yes, in order to make a living for this laboratory, we should have several research projects. So not only by participating to European and international calls, but also to local calls. So you mentioned the project with Irizen, but also now I'm having several other projects going on, for example, with the senior ST, that we call the PPR. So this is very interesting call that help us to buy quite interesting equipment and also to pay PhD students. And with this regard, I am having a project dealing with also with some Italian colleagues trying to make green supercapacitors for the devices for storing energy. And this project would try to make use of this byproduct. Actually, it is waste produced locally in this area from this fruit, argan fruit, because when we produce the added value product, which is the argan oil, it leaves behind a significant amount of byproduct that not used. It is considered as a waste. So we took this as a raw material, as a feedstock, try to make some carbon, some nanoporous carbon, and so we got some innovation here, and we make use of this carbon to prepare some electrode for a device called a supercapacitor. So this is the kind of device that we use, for example, actually for the energy storage devices that use where a significant amount of power is needed. For example, for application like recently, when you stop your car, the engine stop, and you put you start again, and it starts automatically without battery. So it used this kind of equipment called supercapacitors. So this is some prototype we managed to produce from these feedstocks, argan shields. So I'm not going to talk today about this because since it is an ongoing project, but rather I will talk about another valuable resources, which is the clay. So this is the clay we are using. So this is, and I should point out that we get inspired from these people. They are making this handcraft object for the kitchen. So this lady you can see here, this lady, she is trying to, after sieving the resources, so she's sieving and trying to make this object, the ceramic object for the using it in the kitchen. So we get inspired from this technique, and we try to make this device. This is what we call the honeycomb monolith. So this shape is very, as I will explain later on, this is actually, this shape is very interesting because if we want to use some filters or some catalyst, so we need to solve a lot of practical problems and challenging regarding, for example, pressure drop and heat and thermal diffusion, etc. And we were inspired also from what is used actually is in the air pollution, especially for the treatment of car exhaust. So they are using this kind of material called corduroid. So this is the formula. And they are using this shape because they should put it in the muffler of the car in order to treat the gas exhaust and that way. And this material is called the three-way catalyst, because why three-way? It is converting the most significant pollutant that exists in the gas exhaust. So it is called NOx, nitrogen oxide, CO, and unburned hydrocarbons. So through catalysis, these are converted in a non-toxic compound. And to achieve this, so the engineers and the catalyst engineer, they make use of this material as a support for the coating with very active layer. And here we have the engineering of the material that will serve for the catalytic properties. So we need, as we mentioned before, we need some high specific material with high specific surface areas, that mean interesting textural properties. And we need also to put these active phases, such as noble metals, platinum, palladium, rhodium, etc., and with some additives. So this is how it works. So with keeping this in mind, we try to make some equipment based on this. So if we want to have an idea, and for those who are not specialists, how this catalyst works. So if we took the example of the conversion of CO, CO, carbon monoxide, this is a killer gas because it can kill people with the intoxication. So CO, so this catalytic converter is converting CO to CO2 through this catalytic act. So you have here the surface of the catalyst, and we have also the presence of some oxygen. Okay, this red ball. When the CO meets this oxygen activated on the surface of the catalyst, it will be transformed into CO2. So of course we have to engineer here also we have to engineer this catalyst surface as a very active nanoparticles. So here we can see how, for example, the effect of the particle size, gold here, it is gold, it is a noble metal, can get a maximum of activity. So we have to put and to find what is the right size that can give this and then can provide the maximum efficiency of this reaction, the conversion of CO to CO2, for example. So the application, so some rich people, they wanted to use this, who are scared from breathing CO and so from air pollution. So they are trying to paint their houses and to provide a painting based on these materials, because we can make sure that we are having very pure and clean air. So another application, and which is also very interesting for Morocco, is for producing the sulfuric acid, because sulfuric acid need in order to attack the phosphate rock. So and in order to produce sulfuric acid, they make use of sulfur as a raw material, and they need to convert it, to burn it, to produce SO3. But when we burn sulfur, we don't obtain SO3. We obtain mainly and spontaneously, we obtain SO2. So here the catalyst is going to do the job, catalysis, and to convert SO2 to SO3. And this is done using a catalyst based on vanadium oxide. And here I show you the catalytic act for converting, how it occurs, the converting SO2 to SO3, using also some very active oxygen on the surface of the catalyst. So we have the SO2 that meet one oxygen activated, and through this site, active site, and produce SO3. And this is a cyclic phenomenon. So it can be produced infinitely, since the catalyst and the active site are there and they are predisposed and not poisoned. So this is also another issue that the catalysis specialists need to solve, to avoid the poisoning of the catalysis surface, in order to keep this process going and occurring as much as longer as possible. So this is the main challenge if we want to engineer a catalyst material, so we need to find this appropriate support, and we need to appropriate to engineer also the active phase. So sometimes we need also to find out some dopants and some promoters that can help the catalytic act to be as much performance as possible. So this is one picture to make sure that things are real. So here a picture of ruthenium active site with some promoters. So the challenges here, and then mostly it is done at the laboratory scale, is how to achieve the catalyst development with the appropriate structural properties, and also with the stability. The stability, with Professor Khaja the first day talk about the stability. Stability is a key issue in this kind of material. So we have to engineer the material that can last for a long time, because afterwards, so with our friends from the economical investigation, we should give them some very relevant and reliable data that can use to make the business plan and the economical investigation. But this is not the only issue. So here in this slide, I show you the somehow what are the most challenges needed in order to succeed the catalyst design from the active side. I mean, through the life lab investigation to the real application in the industrial process. So there is a tremendous amount of work to do, and not only chemistry and physics and the chemical engineer are required, but also we need various competencies. For example, if we succeed the stability at the lab scale, so then we have to move ahead to another issue to try to solve related to the mass and heat transfer. So we need to shape this material and this catalyst in the appropriate shape. So there is also a lot of investigation through the modeling of the mass and heat transfer, etc., etc. Once we achieve this, then we move to the reactor. So we need to engineer the appropriate reactor. And here also our material should succeed in the being implemented in the appropriate reactor. So there is a lot of modeling, simulation, kinetic studies, and etc. So once we succeed this, we have to move also to the scaling up and the purification and simulation. And this is also, that means we mostly reach promising results to wish an application of our material in the real life. So this is somehow this slide answered the question of asked by our colleague Dr. Al-Misri the first day, who wanted to provide some solution to the politicians. So we need to come to them with the very significant amount of data and also a scenario through various business plan and modeling, including all these calculations that will make us sure that we are covering and we are taking into account all the challenges regarding the application of our materials. So this is just the main challenges associated to this issue. So with this in mind, I will try to cover some aspect from this topic regarding how we can make use of all of this to make our clay as a raw material for using it as adsorbent. First of all, I make use of it in order to to use it as an adsorbent for air pollution containing what we call the volatile organic compound. I will show you some example. Second, I will make use of it as a catalyst for combustion of some air pollution, also volatile organic compounds. And finally, how we can tune these catalytic properties in order to make use of it to produce the so-called syngas. And syngas is very important with respect to hydrogen production, because basically most of the hydrogen produced actually is through natural gas using this kind of methane reforming process. So we can be also, we have checked the possibility of using this material as a catalyst in this at this regard. So this is basically the most important questions I will try to answer during my talk today. Okay. I hope I can move. Yes. So regarding the first point, so this is how we achieve extrusion of the clay. So this was one of my first PhD thesis work. He's Hisham Zaitan. Now he's already professor in Fes. So after him, Sana Al-Harti continued the work. So we managed to, of course, behind there was a huge and tremendous amount of work, because we have tested several samples from our area. And here I should thank my colleague from the geology department at the Faculty of Science of Tetuan, who knows the area very well, and provide me with a lot of samples, so we could test them. And so, for example, here I show some samples I treated here, and we successfully, following this process, as I mentioned to you in the beginning, following what the ladies also were using in a very spontaneous way. But here there is also some science behind this process, how to produce a paste that could stay and can be dried without any mechanical properties, and we can fulfill successfully the extrusion process, because here we have also to recall some rheological properties, and in order to, and here we were inspired from these people. They are working in ceramics, and so we have to achieve successfully a paste that has a liquid limit and the plasticity index between required values. So I use this in collaboration with some colleagues from the University of Cadiz in Spain, which are very close to us, something like 100 kilometers. So we make use of this machine, extrusion machine, in order to produce this kind of honeycomb monolith. So the innovation is usually, if the people the industrial process for producing the cardiolite, they are using very complicated formula, and because they have to use some additives, some liant, and some chemicals in order to successfully achieve the extrusion. But here, the innovation we managed to, as our ladies from the countryside, produce this artisanal object for the kitchen. So they are not using any chemicals. So we follow the same process, and we are not using any chemicals. That means we are following the green chemistry requirement in order to produce this honeycomb monolith. So successfully we produced this patent, and we tried even to, this is why we registered the patent in Spain, because we were having an industrial company that was interested in taking the process and trying to create some startup, but this is very challenging in order to go to the market and try to make the real economy. Sometimes is not easy, but we tried. Okay, so the students get the experience and they are very happy. Another question if we want to answer, because I myself wanted to make use of this shape in collaboration with an industrial partner here in the area, because we wanted to solve one of the issues of air pollution. And of course, we make some calculation and we found that the monolith reactor is better than the fixed bed or fluid bed reactor because of some limitation here. Basically, we cannot use it because of the problem of pressure drop. And here the fluid bed also is not suitable because it's consuming. It has some problems with the material. So that's why we found that using our reactor could be a solution to implement in this industry. So for this reason, we set up, and this is I'm presenting this result to the student, how we build the setup for testing the absorption capacity of this material. So the setup, this is a homemade setup, so we didn't buy it. So we just, at that time, maybe this is something like 20 years ago, I didn't have a lot of projects. So, but the university, they bought a FTR spectroscopy for me, I mean, for the department. So I make use of this FTIR spectroscopy to use it in order to check the absorption capacity of this clay. So for this, we build this part of the setup homemade. We build some system for producing a model gaseous flow containing volatile organic compound amount. We have a system here for controlling the flow, and also we have a system with the oven and the reactor, and finally using IR cell for testing the composition, the chemical composition of the gaseous stream outside the reactor, and what we call the breakthrough curve. So this is a picture from this initial research activity I used at that time. So this is the gas cell. So it is also homemade, and we use it here at the reactor outlet. So this is what we built, also homemade. Okay, some equipment I got from, I bring them in my car from France. So it was a gift from my professor to start research with. So this is the system we use for preparing the volatile organic compound flow and the composition. So here we use the orthoxylene. So this white xylene, because as I mentioned before, this company here was using a lot of xylene in the industrial process for producing the bricks, car bricks. So of course, the xylene was released to the atmosphere. So we tried to find and to study the solution for using adsorption of gases for the capture of this xylene vapor using these clays. And of course, we can even think about recycling this solvent. Why not? So this is the equipment we use, and of course, using FTIR, we need to, in order we should to get some values of the absorption capacity. That means we have to do some quantitative measurements. That means we need to calibrate the instrument. So this is for the students. want to build the setup and make calculation of this. So very easy, basic work of Beer-Lombard law in order to get the quantitative response of the equipment. So this is how we do it. So this is the IR spectra we recorded at the outside, the exit of the reactor. So we can start at the beginning. There were no xylene because all the xylene is adsorbed. But after saturation after saturation, we start having the breakthrough of this solvent. Okay, so like this. Okay, when it is saturated, so why not? We say, okay, we can also try to dissolve this and to perform and to carry out an isothermal dissorption. So okay, here and then we can carry out what we call the TPD, temperature programmed disruption, and then we explain later on why. Because so if you want to have an idea on how this is what we call the breakthrough curve. So at the beginning, all the vapor is adsorbed, but following the saturation, so the signal is we call the breakthrough. So if we calculate and we integrate this area, so we can get the value of adsorption capacity, and we can make a lot of calculation using this kind of result. So this is yes. So this is basically the breakthrough curves we obtain, the equation we use to get the value of this vapor adsorbed by the clay. And here, once it is saturated, we stop the gas and we change to the neutral gas. Here it is nitrogen basically, and we found that the xylene is weakly adsorbed, so it comes to 0. But when we make the balance, we found that still we cannot recover all dissolve all the xylene. That means it remained. So when we heat the orthoxylene dissolved from the clay, that means it was more strongly adsorbed. So we thought that we could make use of this data and some thermodynamic parameters in order to measure and to give values of the heat of adsorption and dissorption. So this is why, because the clay, if we try to explain why we have this difference in terms of adsorption capacity and adsorption energy value, because this is due basically to the textural and to the porosity of our clay. So here, from this nitrogen isotherm, adsorption isotherm. So we are having now we are having this equipment. So I think we were lucky to have it maybe since 15 years ago. So we can measure the adsorption isotherm. We can get values of surface area and porosity and all of this. This is because this is very crucial. Textural properties is very crucial for studying the material stability and the material performances. So we try to, this is what I said before. So if we measure the total amount of the adsorption capacity of xylene, so this is the value, and we can measure the reversible adsorption fraction and also the irreversible. So most of the xylene is reversibly, weakly adsorbed on the clay material, and only 30% of micromole per gram was more strongly adsorbed. More strongly adsorbed, that means it was basically because if we look at the textural property, that means we will have some as Dr. Khamlish explained this morning, this is it can be explained with this potential wheels, and I will explain later on when I come to this. Yes, this is the point. So this is the potential wheels involved. So if we can Leonard Jones diagram, and we can find that there is various type of potential within the surface of catalyst of adsorption. So this is basically for the weaker adsorption, and of course the species that are. But here I'm not talking about chemosorption because we don't have the the bonding. So this is just because we are having narrow pores within our material. So we can make use of some thermodynamics in order to make to try to measure and to give an estimation of the adsorption energy of the xylene involved in this process. So if we wrote this, this is basic thermodynamic laws regarding the equilibrium and the chemical potential between gas phase xylene and adsorbed. So we can get to this famous equation, the so-called Clausius-Clapeyron equation. So we can, by changing the partial pressure and the temperature, so we can get the value of the energy. So experimentally speaking, that means we have to measure isotherms. So this is what we did. So we can get different isotherms. That means we should fix the temperature, changing the pressure, and measuring the adsorbed amount. We can do this at various temperature. So we can get here isosteric. That means we will fix the value of an adsorbed amount, and we get experimental isosters by measuring this as we did here. So we can figure out the tremendous amount of results, because here the PhD student, that means 1 point is 1 day. 1 point is 1 day experiment. Yes, to get this. And in order to feel all these, so we can measure this, get this very important results. And later on, we can measure this isoster. And from this, experimentally speaking, we can extract the value of the isosteric heat of adsorption, and we can get this from different surface coverage, and we can found here, for example, it change depending on the surface coverage. It can change from 40 to 44 kilojoule per mole. So this is regarding the weakly adsorbed species. So in order to measure also to have an idea on the more strongly adsorbed species, so we make use of this very well-known equation called Sevantovich, and this is for TPD, temperature programmed desorption. So we can measure for different heating rate what is the temperature maximum for the desorbed species. So if we get this with the heating rate and the TM, the temperature at maximum, we can make of this, and we can extract values of the heat of desorption. So we did it, and we get values of this. So that was amazing and interesting, and we get several publications. So we published the results, and of course, also some of the results were highly cited. So this paper was cited around 150 citations up to now. So there is also some other publication regarding the choice and the selection of these clays, and also the exclusion of these clays. Okay. Now I will move to another question regarding the catalytic properties of our clay. So when we look at the chemical composition of the studied clay, so we found it has silica alumina, and these materials are usually used as a catalyst support. Also, we have some other significant amount of iron, potassium, magnesium, etc. Especially iron is used as active phase in catalysis, and the potassium, magnesium is used as a dopant. So this is a material we get for free from the nature. We get it there, and we say, okay, this can this can, maybe it can work. It can have some intrinsic catalytic properties, because people in the laboratory, they try to engineer this active material, doing a lot of work, but we found that maybe our system, thanks to this chemical composition, can work maybe. So we tried to investigate the intrinsic catalytic property. Why? Because also, and regarding the stability of the material, so it was the chemical composition and structure was stable. So we measured the XR, the fructogram, by increasing the temperature, as shown here, and from room to 500 degrees Celsius, it is stable, and it doesn't change. That means it can perfectly work as a catalyst because it is stable within this, at least within this temperature range. So this is why we decided to, use this system as a catalyst, as material as a catalyst, and try to study the catalytic combustion, the catalytic oxidation of several volatile organic compounds. So this was another PhD thesis, and we tried several compounds, and the combustion, the catalytic combustion, catalytic oxidation of this material. And of course, using the setup I mentioned before, and of course we use also, as I mentioned before, IR as a analysis technique for following and monitoring the conversion of these volatile organic compounds. So we can see, for example, here the IR of the different studied compound, and we can see what is the area that we selected for performing the analysis. So because here we are talking about quantitative use of IR. So at the beginning, I had some problems to make this publication accepted, because most of the scientists, they say, okay, IR, we use it only for identification and not for doing the quantitative analysis. But at least at the end, they were convinced that it was possible, and it can also give some interesting information, because instead of using, for example, gas chromatography or mass spectroscopy, here we can have in one spectra, if there is no overlapping between the iron bands, so we can follow in a very efficient way the conversion of the different the study in volatile organic compound. So here I show you the one example of the CO oxidation to CO2, and how we, by using FTIR, we can follow the CO conversion to CO2 at different temperature. This is what we call the light of curves. That means we increase the temperature and we see how the catalyst behaves here. So if we study the behavior, the profile of the light of curves with the empty reactor, sorry, it is in French, but we know that would say in English. So this is the profile of the empty reactor, and this is the profile of the reactor with the clay monolith. So we see that we significantly lower the temperature of the total conversion of for example, here it is a CO. So that means here we are talking about a gas phase total conversion and oxidation of CO that needs around 700 degrees Celsius in order to convert CO to CO2, only in gas phase reaction without contribution of the clay material. But when we put the clay, we lower the temperature. Here, for example, we can start about converting to 250 almost, and start having total conversion of CO. So this was very interesting. So the same thing happened with the other studied compound here, the different studied compound, and yes, and what we found that the clay was very interesting result with respect to N-butanol conversion. So because we see here, it lower significantly the temperature of total conversion of N-butanol. So for this reason, we try to understand how this clay behave as a catalyst. And we try to compare and to compare the catalytic performances to others material. For example, here we compare it with this is the clay system. This is the profile of N-butanol conversion. And we use, for example, cobalt oxide or iron oxide alone. Okay, so still our clay give better result than the cobalt oxide. I mean, the cobalt oxide here, we tested a cobalt oxide coated, deposited on the stainless steel plate using this technique, CVD reactor. So this is the process how we use it in order to deposit the cobalt, iron oxide, etc. And this is the result, the behavior with the empty tube and the cordiorite. So we see here the cordiorite almost responded as an empty reactor because this is a very neutral material. But our clay is having some intrinsic catalytic properties. So we tried also to understand why. Here, for example, we put also, is this due to the shape? Because with the powder and here the monolith. So the response is almost the same. The pellet, the monolith, the powder, and of course still better than cobalt, iron, and also cordiorite and the empty reactor. So this is that means our clay material must have some intrinsic catalytic properties. So we tested also another issue is when we coated the clay, since the cobalt oxide gives very interesting result, we coated the clay with the cobalt oxide. Here we found, in this case, the clay covered with the the cobalt oxide gives very interesting result. That means there is a synergy between the cobalt and the clay. And this is why we get even better result than the clay. So when we try to explain the reason why, the reason here, if we compare the XRD of the clay alone and the clay coated with cobalt, here, monolith, cobalt, and cordiorite. This is. So we found a very interesting result. That means we found that we obtain lower, smaller particle size of cobalt on the cobalt oxide on the monolith. So we explain this result. That means if we put this possibility to tune the catalytic performances of our clay material by adding some appropriate active phase, as we have shown here in this result, using, for example, cobalt oxide. So with this in mind, say, okay, now we can try to make use of this finding in order to tune the catalytic properties of this clay material towards another reaction, which is methane reforming. And why not for hydrogen production, Fischer-Tropsch or other process. So this is what we. Okay, I have to move here. So this is the results are published for those who are interested. Yes, this is the issue I am going now to talk about, is how we can tune the catalytic behavior by adding some appropriate active phase and promoters in order to selected dry methane reforming because we were thinking about using biogas since we don't have up to now, natural gas in Morocco. So we can have methane for free using biology and some anaerobic digestion of the waste to produce the bio waste. And the biogas, it has methane and it has the CO2. So we can get those, the both of them as a raw material. So we can solve also the issue of this global warming, and in order to produce this very important syngas, hydrogen CO. So we can also improve the catalytic performances by adding some oxygen, what we call partial oxidation. Okay, so this is what we call the autothermal reforming, because this process here is very endothermic. So there is a possibility of making use of the renewable energy in order to start the process, because endothermic is here. But if we want to make it autothermal, so we need to adjust a little bit some thermodynamic parameters with respect to the oxygen addition and the steam reforming also to make it autothermal. In order to successfully achieve the catalytic performances, the challenges is regarding the stability of the CH bonding and the CO bonding of these feedstocks that need really appropriate catalyst, because otherwise we will have this very difficult poisoning problem due to the cooking, the carbon deposition on the catalyst surface, and then it will poisoning all the active site, and we'll have the problem. So we need to engineer in an appropriate way the catalytic formulation to achieve this and to solve and to overcome this challenging issue of the cooking. So this is usually done by using some noble metal, ruthenium, rhodium, palladium, etc. But this is very expensive. So this is why nickel started also to be used at industrial scale because of his price. You can see here the price of nickel. It has nothing to do with the prices of platinum, palladium, rhodium, etc. So this is a very noble metals. Of course, they are having very, very interesting catalytic properties, but the price is there. So the industrial people, they need to association of the performances and the cost. Cost should be also taken into account. Not only nickel, but we need also, industrially speaking, so they use also magnesium oxide, which is also very interesting because it provides some, as we will show later on, some basics site which are very interesting with respect to the absorption of CO2 molecule. So this is the issue and the challenges we should face. So we have to succeed first to find the catalytic, the chemical composition that provide higher catalytic performances using nickel, and to some appropriate water, and also not only achieved catalytic performances, but also the extrudability, because we wanted to avoid. So we mixed all these catalytic formation together because we wanted to avoid the deposition of this layer, because industrially speaking, they are putting this coating with the layer with the active phase and the catalyst support. So we didn't choose the solution. We just wanted to find a formulation using the clay and without deposition of this layer, because it has some challenges also associated with the use of this layer. So this is what we try to do. So a huge and tremendous amount of work has been carried out, first using the powder, because we need to find the composition of the clay and also the appropriate promoter, and then to try to extrude afterwards. So this part of the result was done in collaboration with the University of Poitiers in France. And now the PhD student successfully finished his thesis, and now he's working in China, Academy of Science. So he successfully managed to produce this paste using appropriate formulation of nickel and magnesium iron, and to extrude it as honeycomb monolith. So before having this, this formulation, I will take you to the journey, how we did this. So the journey starts from, first we have to find the amount of nickel, and what is the appropriate amount of nickel that should be used and that lead to the better and the best catalytic performances. So this is one issue. Here you see, for example, by using this mixing, I show you, that means we can also fix a value of nickel and the dopant, and we can say by mixing this, no problem. Even at the surface, the composition remain not so different from the blue. So this is the performances we obtained by performing the catalytic test. So by using the nickel and cerium is very important because it's very sensitive to oxygen. And here we are going to talk about the oxygen mobility. So the best result was given by this formula. See here? Yeah, but unfortunately, after a certain time of testing, the activity of the catalyst decreased. We lost the activity. So that means why? So we try to find the reason. So with cerium, after, for example, 24 hours of reaction, we found at the end that there is the formation of this species on the catalyst surface, and we suspected this species as responsible of catalytic. Because we're talking about restructuration of the catalyst, and we lost the performances, and the performances due to the formation of these iron in Italy species. So the result was published here in this, and of course, why? Because of the size of the particles involved in the process. So we solved the problem here now by changing the cerium to lanthanum, and lanthanum solved the problem of the desactivation after 24 hours. So even after 24 hours, the lanthanum, we use it as a promoter. So we don't have desactivation of the catalyst, but we couldn't succeed the extrusion because we have some mechanical properties, some mechanical problems. So here we show that with lanthanum we managed to reduce the particle size, but unfortunately we don't succeed the extrusion. So this is why we changed to it. So the result was published here with the lanthanum cerium system. So I was happy because some colleagues from Qatar University, they just get the notification. They cite this work because they are carrying out some similar research. So in order to solve the problem with the lanthanum, because although it is having allowing higher activities, but we didn't succeed the extrusion. So we changed now the lanthanum to magnesium, and we managed to extrude using this formulation some honeycomb monolith. Because of the nickel, it changed the color. So we got the formulation, and also we got very acceptable mechanical properties. Okay, even after calcination. So as I mentioned before, this has been done in France with the colleagues from Poitiers, and with magnesium, we found that there is a formation of a kind of solid solution, magnesium in EO2, that prevent sintering, sintering of the catalyst, and that because the challenge is to maintain the site and to find the chemical composition that allow the appropriate site. The particle size. So here we can take a picture here, this image of this solid solution will form the catalyst surface with the magnesium and nickel, and with appropriate, see here. So we can have, when we add magnesium, this appropriate amount of magnesium, we reduce the particle size from 37 to 9.5 nanometer, which is, and we say that the best catalytic performances observed, of course, are responsible for this lower particle size of this solid solution we form with the nickel and magnesium at the catalytic surface. So this is the performances that shows that, yes, we have. And another important thing here is regarding what is allowed also by the use of this magnesium. And you see here we provide, when we've done the measurement of CO2 absorption and desorption, so we can make a kind of quantification of the basic site involved in this catalytic act. And we say, okay, see here with the 8% of nickel and 3% of magnesium on the monolith, we provide the higher amount of basic site at the catalytic surface, evaluable for the catalytic, for the production of syngas using methane and CO2.
Prof, you have 15 minutes.
I will conclude. So this is the site. Here the quantification of the basic surface site involved in the process, and you see here in terms of surface state density. So we provide the most higher number of sites available for producing this syngas, hydrogen and CO, which are very important. So here I will just summarize all the concluding remark as I mentioned before, and finally I will, yes, this is for those who are interested in this work. Just there is a published paper here, and finally I will acknowledge all the projects involved in this. Basically, a lot of international cooperation projects. Since 2000, we are working in this, starting from the project I obtained with my former laboratory in Lyon, France, to some other project I got also through Morocco, Germany, from colleagues from Bielefeld. And of course, so I acknowledge here all the involved PhD students and the colleagues that help us a lot for developing this research. Thank you very much for your attention.
Thank you, Professor Tariq Shafiq, for your valuable presentation. Yes, Prof. Ahmed, do you have any comment before opening the session for the question and comments?
Yes.
Yes, please.
Thank you, Professor Tariq. There are two things what I would like to hear. One is what is the contribution of your research from Erizen? I don't hear this. If this has helped you, and the second is what you are going to do for the syllabus, when and how and all this stuff. It's very important.
Yeah, well, I think Sahmed had these two questions were not involved in this lecture, so I can answer you. Yes, with the Erizen, actually it was a research topic I mentioned this morning, dealing with another project. Okay. This is regarding the production. This is regarding the production of these nanomaterials for lubricating system. So here, if you want, catalysis was not involved in this research because basically it has to do with the production of nanoparticles, as I mentioned before, to control the shape, to control the morphology, to control also the stability. So all of this at laboratory scale was an issue. And yes, I should thank the ERISAN for the financing this research, and we got very successfully and a lot of publication through this research, but at laboratory scale. But if we want to scale up the research at a higher scale, it's a very complicated issue. As I mentioned with Professor Talib yesterday and Dr. Khamlish this morning, scaling up nanoparticles production is not an easy issue. So we are still trying to find some very, affordable and possible technique that can also, why not, help producing in terms of economically speaking, because when we make the calculation for the nanoparticles we produce from this project, it is the cost, if we based on the result we obtain at the laboratory scale, the cost of production is very high. So we cannot translate directly this result from the laboratory to the industrial application. We need to perform some very appropriate scaling up procedure that will economically speaking allow transfer to the industrial scale.
What about the syllabus? Can you explain to the student what you are going to do, and when you want to start to teach and all this stuff?
Well, I cannot answer this question today, Ahmed, and we are actually
what you are going to do when you start. Forget about it, but because students they want to follow your course and they want to know what's that and what they have to know before
hopefully second semester, because
yeah, it's fine,
yeah,
but
so we need
they need information about your course. What do you have to teach? Like the other guy, what he did.
Yes, I can provide information when available. Right now, I cannot give them a very precise date, but could be done mostly during, because Ahmed, we are teaching in French, and if we
I think you don't hear me very well. I am not talking about when you start. I am talking what do you want to give information only about what you want to teach.
Well, okay.
It's not for me. It's for the student.
Yes, the students. Okay, if they are interested in catalysis, so we can see how much people they will be interested in catalysis. So as I mentioned last time, basically we will talk about heterogeneous catalysis. You see, and the basic concept of heterogeneous catalysis and how we can use this kind of catalyst material in the energy field. So producing, yesterday you sent this movie regarding the Fischer-Tropsch process. So I have, for example, some comments, although I'm not working on this issue, but we can teach the student basic concepts that are used for the producing this kind of biofuel.
Okay. So I want to thank you very much about all this very important research, which show your hard work. And I would like to show here some video which is related to your course.
So before, maybe excuse me to interrupt you, because maybe some students are interested to ask some questions.
No, I will start with this and then the questions.
Okay.
The sound, Professor Ahmed. Still not working.
So, Professor Ustaz Saleh, do you see the video and do you hear it?
We don't have. I think the sound is not activated. Maybe.
Yeah. Or
so, I think everything is open. We have just to make the stuff working, and that's it.
I will try to open it from my side. I will check.
No, you don't need it. Don't need it. Otherwise, we will make everything completely lost. Huh?
Okay, so let's.
So let's do first some paper chemistry. What is the Fischer-Tropsch reaction?
So do you hear now the song?
No, Professor Ahmed.
Please?
No.
Gives you a range of products, fuels.
What about now?
Chemicals.
We hear the video. It is not there.
In general,
the video is not there.
What we call
Yeah.
hydrocarbons.
Yeah. Okay.
Why is this reaction now so?
Yes, it comes and now you closed it. Yes, but waiting for the sound after a few seconds. Yes.
So let's do first some paper chemistry. What is the Fischer-Tropsch reaction? The Fischer-Tropsch reaction is the reaction between hydrogen and carbon monoxide. Both together are called syngas, which gives, when you use a catalyst at a given temperature and pressure, gives you a range of products, fuels, chemicals. In general, it gives you what we call hydrocarbons. Why is this reaction now so interesting? Well, let's first look at the syngas. Where can it come from? It can come from different sources. For example, it can come from coal. Coal to syngas is a known process. Very interesting nowadays is when you use a renewable source to make the syngas. For example, waste biomass. If you convert it in the right way, you get a gas, exemplified here by this balloon containing hydrogen and carbon monoxide, the syngas. When we have that gas, we can flow it over a catalyst, shown for example here for an iron catalyst, and it gives you then a range of products depending on the catalyst temperature and pressure. For example, you can make clear fuels, and you can make all kinds of plastics. Okay, well here we have two burning liquids. On the left side we have a Fischer-Tropsch liquid. On the right side, this one, we have a liquid based on natural crude oil. And what you see is when they burn that this one, the natural one, gives soot, it gives a black vapor, and the flame is a little bit more yellow, meaning it burns more dirty than the Fischer-Tropsch one, which has a more colorless flame and gives you less soot.
test the catalyst, we have to use a reactor. We put the catalyst inside. Then we place this reactor in an oven. But what you can see here, the gases we feed from this side, from these valves, to the reactor. So here you have hydrogen and carbon monoxide coming in, so synthesis gas. And at the other side, this side of the reactor, you get the products. The products are in the gas phase, so we cannot see them, but we analyze them with gas chromatography. In the end, what you can see is the composition of the gases coming out of the reactor. From the Fischer-Tropsch reaction, we can produce fuels, but we can also produce chemicals. In this case, we are using a process to convert synthesis gas into lower olefins. Lower olefins are the building blocks to produce plastics and many other chemicals. So effectively, what we do is we take waste biomass, convert it into synthesis gas, which is a mixture of hydrogen and carbon monoxide. Then this gas is put in contact with an iron catalyst. This catalyst was produced here in this lab, and there is a paper related to this work in the Science magazine. From this process, we can obtain the building blocks for the plastics, that is the lower olefins, which means that we can produce green plastics, normal plastics from waste biomass.
Okay, from my side, I'm ready. Can you hear me?
Yes, we can hear you.
So now the reason why I show this video, because we want to make people seeing exactly in a small summary of the talk or some very basic issue of the talk of Professor Tariq, and that they can ask and they see exactly concretely what's going on. And this field is very important for our countries, the catalysis and the heterogeneous catalysis especially. And I want to thank again Professor Tariq, and now I give the floor to...
If you allow me to comment a little bit about this process, Si Ahmed.
Yeah, do it.
So I don't know whether Si Khamlish is still with us because
yes, I am with you, Prof.
Yes, I think maybe he can comment also on the use of Fischer-Tropsch process, because actually this is the process that saved South Africa when it was under embargo, because you remember at that time South Africa couldn't do business and couldn't also have oil for running the cars. So at that time, but they have a lot of coal in South Africa, isn't it, Saleh?
Yes, actually, yes, in South Africa, they moved toward that technology due to the lack of oil. And remember, in South Africa, they had what we call apartheid that time.
Yeah, apartheid.
Yeah,
Yes.
and the world, they were not allowing them to make business with other countries.
Exactly.
So they decided to go for that process.
Exactly.
So that is the reason, yeah.
So this is, I remember my PhD thesis when I started first in France. So they were also trying to find this artificial way for producing hydrocarbons and using Fischer-Tropsch process, because at that time the solution was through gasification of coal, you can get the syngas, CO hydrogen, and through Fischer-Tropsch, because it was first developed in Germany after the Second World War, they produce the oil and fuels. And now this process could be also a chance for us in the Middle East and also in Morocco, because since we are planning to use hydrogen and also green hydrogen. When we are talking about green hydrogen, that means hydrogen is going to be available, and the cost of hydrogen is not going to be very, very significant. And of course, hydrogen, it has these problems of transportation and the storage, etc. So the best way is to try to convert it in some added value product. And here, Fischer-Tropsch could be a solution, as it was for South Africa, because it helps them to transform coal from a solid fuel to a liquid fuel and to use it in cars, for example. And also this process, it has the merit, one other additional advantage, and why it could be used also now as a solution, because it can produce a very pure hydrocarbon, similar to the kerosene for the planes, because you know, for the petrochemical refinery industry, they need to get right from the sulfur and through some additional processes such as hydrodesulfurization to remove the sulfur and to make the sulfur content very low. And here the catalysis also is doing the job. And Fischer-Tropsch, because using CO and hydrogen now from biomass, as the professor explained in the movie. And by the way, I will thank very well Professor Nawi for choosing this video, because it is really meaningful for us. So biomass or coal, we can get gas synthesis, and through Fischer-Tropsch we can get on to the oil, and very pure and high quality oil. So like this, we can have a very, very important added value product like kerosene, for example, and could help instead of thinking about how to store hydrogen and how to transport hydrogen. We can make some kind of refinery locally to produce kerosene. So we have to control and to master the technology, the know-how, and also to make the business plan, to make the production price competitive with what is existing in the market. So this is what I wanted to point it out with respect to this topic. Thank you very much.
Thank you, Professor Tariq. Yes, Professor Ahmed, want to add something?
No, just I have some reason to present this video, because I thought it can open some. It's very important. It has a very important issue. That's why I did a little bit. I put it by like if I make it رغما عنكم, as we say. But I think I have a good meaning. It's not for just. It's really to yes.
كاين واحد في المثل في العربية يقول مصائب قوم عند قوم فوائد.
It has nothing to do with what we are doing, but anyway.
هذا هو علاش هذاك Fischer-Tropsch نقدت جنوب افريقيا.
Yeah, I know.
هناك بعض الدول جنوب افريقيا، ماليزيا، اللي هما حاليا هما الليدر في هذه التكنولوجيا. the artificial trap.
I think the most important is to see what we can do from this process now, because as you say, we want to produce green hydrogen, and we want to mix it with CO2 to make,
Yes,
for
CO2.
example, methane,
Yes.
or to mix it with ammonia to make fertilizer.
Yeah.
That's two things very important for Morocco. And this is, I would like to see professor from university to get into this field.
We can prepare lectures on this maybe in the future.
Yeah. Anyway, the students are waiting for your course, because your course, the course of Dr. Khamlish, the course of Professor Ben Youssef, the course of Talib, Professor Talib from Paris, are really a core courses. I am thinking about in the virtual learning university to make a core courses. This means a course which is obligatory to make if you want really to go to something else. And that's why I try to make people aware of this. Okay? So now I give the floor to Ustad Salem if there are some questions in the audience.
I think Professor Saleh Khamlish wants to comment also. Please, Professor Saleh.
Thank you very much, Dr. Salim. Actually, I don't have a question, I have a comment about the fantastic work that Prof. Tarek shared with us today. It's a very fantastic and I'm really happy to see this kind of developments going on in Morocco. And by the way, of course, this process, it's very fantastic. And during his presentation, I heard that nanoparticles are very important in this process. And also I heard a comment that there are heavy limitations in terms of upscaling the production of nanoparticles in general, as catalytic nanoparticles. So again, I will repeat myself, for the upscaling of nanoparticles, I think we can go back to the laser ablation. I think that process, it will allow, I'm pretty sure that it will allow production of noble metals or catalytic nanoparticles in general at a higher scale. So I will be grateful in the future maybe to get in touch with you and Professor Talib and other interested professors from Morocco, so we can link between each other and to find out how can we involve this technology in this kind of developments that you are carrying on in Morocco. And thank you very much for this interesting talk, and I hope that we can continue on this kind of technologies. Thank you very much.
Thank you.
Thank you, Professor Saleh. Yes, please, Prof. Ahmed.
Yes, if you allowed me, both of you, Tariq and Saleh and everyone here, he's interested. I think it's very important just to present a project to Erizen call about startup, not R&D or fundamental, or a startup to develop this laser ablation to prepare nanoparticles, a special nanoparticle for a given application. You can do this. You start to have the project, and we will get in contact with Erizen to make it running. This means in this project you can buy this setup to make nanoparticle. You can have a place in Ben Greer, a small company, and you can develop this.
Exactly, Prof. Yeah, I agree with you. And currently, actually, I'm working on a proposal that I will be sharing very soon with interested researchers from Morocco, particularly Professor Tarek, yourself, Prof. Ahmed Nawi, so we can be able to finalize it, and so we can submit it as soon as possible. I agree with you, and thank you very much for your advice, Professor Nawi. Thank you very much.
Me, I cannot be there because there is a conflict of interest. I'm supposed to judge this project afterwards. So therefore, I cannot, even the day of we have to decide, I will not be there because I'm already in contact.
What I will ask kindly, because Professor Talib, I know his work very well. He's
No,
working
you don't get what I'm saying. I am in the president of the Scientific Council of Erizen. This means there is a scientific council. When the project come to Erizen, I have to read your project and to decide, to give you marks and to see, yes, this project has to be financed or not. Since now I know you and we have discussed it, this means I am a conflict of interest, and therefore I'm not allowed. That's what I mean.
Okay. So I will communicate with Professor Tariq, and also I mentioned about Prof. Talib, Abdel Hafid Talib from France, because he is one of the best experts in nano, as he's a Moroccan scientist. I hope he will accept to cooperate with us regarding this
great pleasure
of laser ablation and producing nanoparticles at high scale.
With great pleasure.
Okay.
So just a few.
Yes.
Ustad Salim.
Yes. Just I wanted to tell the Professor Abdel Hafid that to have a talk or a comment on what you are saying. Please welcome Professor Abdel Hafid.
Yes. So thank to Professor Salim Kemish for his invitation. It's my great pleasure to take part in this collaboration. I think in the past, Salim, we get in touch, we did some attempt to make something. I think now it can be a good occasion to continue what we started to discuss. I mean, maybe 1 or 2 years ago. I don't remember. It means maybe it's 1 year.
Mm-hmm. No, yeah, you are right, Prof. Talib, you are right. And we apologize. Things were happening and with the COVID and so, but anyway, as I mentioned, I'm working on a proposal that I would like to share with you and Prof. Tariq, so we can apply maybe through the Erizen, and we can have a laboratory maybe in Morocco where we can produce nanomaterials at a higher scale. And I believe your involvement, yourself, Prof. Talib, and Prof. Tariq Shafiq, it will have an impact on the success of the proposal, so we can carry on that business there in Morocco. And yeah, it will give me a huge pleasure to contribute from my side.
From my side also, I can share all the experience we had with this Erizen project, and to share with you the good and the things we should avoid in order to make this collaboration successful. Yeah, thank you, Saleh, for your invitation. Thank you very much.
Thank you.
And also thank you, dear Professor Talib, for also your participation.
Thank you.
Thank you all, and this is a good conclusion and a good step to move ahead. This is what we needed. Right, let's see others if they want to participate or they have comments or questions. Please, time it's there. You can have your questions or any comments. All, or we can close this session. Nobody there. Okay, Prof. Ahmed, before you conclude, I think we give Professor Tariq a conclusion from your side, please. Yes, please. Professor Tariq, what do you want to say before ending?
أنا أتكلم بالعربية حاليا لأن أظن أن الحاضرين هنا أكثرهم عرب.
صحيح.
أول حاجة أود أن أشكرك أنت على مساعدة في توفير اللوجستيك وفي إدارة النقاشات بواحد الروح الرياضية وبواحد الأريحية. وأود أن أشكر أيضا أستاذنا الناوي على نصائحه وعلى أخذ هذه المبادرة، لأن حاليا هذه المبادرة أخذت كثيرا من وقته كي يجمع ويتصل مجموعة من الأساتذة. أتمنى أن نكون عند حسن ظنه، وأن نعمل جاهدين على إنجاح هذه المبادرة، وسيجد من عندنا السند والدعم الأساسي لكي نطور هذه المبادرة وتكون حقيقة منارة وإشعاع ومثل يحتذى به في عالمنا العربي. شكرا جزيلا.
شكرا لك بروفيسور طارق. إن شاء الله بإذن الله تعالى تتحقق كل هذه الأماني والطموحات بتعاون الجميع، فكلنا نكمل بعضنا بعضا في هذا الجانب، وهذا ما نهدف إليه. شكرا لك وشكرا للمحاضرة القيمة المتميزة صراحة التي قدمت اليوم، وشكرا أيضا لأخي البروفيسور خمليش أيضا في لمشاركتي في هذا اليوم. دكتور بروفيسور أحمد, if you give us the coming lectures, please. Go ahead, please.
Yes, you see it on the screen, I guess, no?
Yes, it is there.
Okay, thank you very much. So, of course, I'm very happy to work with good people. And when I start this virtual university, I don't ask only some people, I ask the good people. And I have, every time I talk about Tariq, about some people in Morocco which are very good, because we observe them since 2011 when we start in Erizen. We know who is working and who is not working, who is teaching very good, who is not. We know everything. And therefore, I ask only good people. And now we move to another good person. I know him, I think last year, is Professor Daffy. Is Professor Daffy here?
Professor Daffy, let me check. No.
Okay. So I know last year he invited me to a series of talks, of conference at Mohammed VI University, and it's a very known conference which is around phosphate, and I give this talk, and afterward we had a very much discussion. He is a very good scientist, very well engaged in the Moroccan resources like phosphate, etc. And tomorrow he will talk about the topic, which is it's written here in French, but he told me he will speak in English. So it's about phosphate, the exploration of phosphate, the Moroccan deposit, and he will give, as he told me, an interactive talk. This means maybe during his talk he will communicate with folks, with audience. So this means Ustad Salim, tomorrow you will have some job to do. Sometime you will during the talk of Daffy, you will open sometime the microphone, maybe the video for audience. That's what I understand from his WhatsApp when we discussed with him. So I told him from here he is welcome for tomorrow at 11 a.m. And I want to thank everyone here for listening, and I hope we will have a lot of people tomorrow to see about the resources in Morocco, in the raw material in Morocco, and how we will use it, etc., etc. Thank you so much. I will stop my presentation, and I think you have the last word, Ustad Salim.
The last word, it's yours, and really thank you all. Thank you, Professor Abdel Hafid Talib, for your participation, and also Professor Saleh there. We will see you, inshallah, in the coming lectures. So everybody, I wish you all the best and good luck. مع السلامة إن شاء الله. مع السلامة.
السلام عليكم.
وعليكم السلام.